Hi everyone, today we're going to be doing the final review for EE471. So we're just going to go through all the topics we should be familiar with. And so what we're going to do basically is first we're going to start out with state space. So state space, the main thing about it is why we like state space is because we can describe a set of internal variables called states. And so we can represent like a higher differential order equation with a set of first order differential equations. So you can represent a higher order differential equation with a set of first order differential equations. Okay, so the main way how we're used to seeing our state space representation, a lot of times it basically has the following format, where we have a vector derivatives of our state variables, and then it's equal to, and then there's system matrix, and then we have our states. These are usually like a column, and then we have our input vector B, and then our input here. So sometimes this is like U or R, depending on the scenario. And then we have our output Y of T is equal to, and then we have our output vector C of T, and then we have our state vector X of T, and then plus, and then here we have our feed forward gain, and then DUT. So a lot of times, just making sure you know how these parts work if he were to ask you about it, is that making sure you're familiar with this type of terminology is that right here, it is our state vector. So if he gives you a state vector, you know what that means. Here for this is our input right here. So this is what we have as our input, the U representing like the input coming in. And then this is known as our system matrix, A here. So describing our entire system. Then we have B here, which is called the input vector. So that makes sense. It's right next to the input, so it's called the input vector. Then we have the output vector here. And then we have the feed forward gain. Notice that D is a scalar, it's not a vector. So this is known as the feed forward gain. And so basically what we have now is our entire matrix here. This is just known as your state equations. And this is known as your output equation. And the two of them together make your state space representation. Okay, so that's what we see here. And so what we're going to start out with is we're going to try and find the state space representations for one of our systems in order to try and derive it. And so what we're going to do is looking at the following system. So it's an RLC type of network. So here we have a voltage source. So for our first example, and this voltage source is going to be V of T. And then we have an inductor here. And then we have a resistor. Then we have a capacitor. So what we're going to notice here, basically within our system, is they're going to define the current going through the inductor, IL of T. They'll have the current running through the resistors, IR of T. And they'll have the current running through the capacitor as IC of T. Okay? So what we have to do here is we have to determine how many state variables we have. And what do we choose as our state variables? So you want to choose your state variables as something that's not dependent on something else. A lot of times we like to choose like the voltage in the capacitor and the current in the inductor because they're independent of each other here. The big thing though is we have to determine how many state variables we have. And so how many independent storage elements do we have? Counting right here is that we have one storage element. The inductor stores energy in its coils, the magnetic field. And then here, capacitor stores energy in its electric field. And so these are two storage elements. So we have two state variables. So two storage elements, two state variables. And so now that we see that, what I'm going to choose, because by convention, we just have to choose two state variables that are independent of each other. So my first one, my x1 of t, is going to equal the current going through my inductor. And then my x2 of t is going to equal the voltage on my capacitor, okay? And so those are my two state variables. Now that I got my two state variables, what I'm going to do is I need to find x1 dot and x2 dot. So I need to find the derivative. And so what you sort of need to remember here is recall that there's the mnemonic Eli the Iceman, and that works honestly for this application. So remember how the voltage in a capacitor sorry, wait, ice. Yeah, sorry. Wait. The current in the capacitor, which is your IC. So I is equal to C dVc t divided by dt. And the voltage in an inductor, so voltage in an inductor is given by this equation. So I equals C times dV dt, and then Eli E equals L di dt, because E was the old notation for voltage. And so this gives us what we can represent them for the derivatives of our state variables. We know this relationship for the capacitors, the current's described by the following equation, and we know that the voltage for an inductor is described by the following equation. But notice that the derivatives of our state variables. So here, this gives us the current going through our capacitor, and this gives us the voltage on our inductor. And so what we're going to notice is, isn't the current in the capacitor, we can write a Kirchhoff's current law here to describe this. And so don't you agree that the current from the inductor is equal to the current going through the resistor plus the current going through the capacitor? You can write a nodal analysis, sorry, right here at this node, you can say that the current going in is equal to the two currents going out. And so what I'm going to have here is that the current going in, I of L, is equal to I of R plus I of C, right? At this point, IL is coming in, these two are going out. And so right here, what we're going to notice is that you can plug in your I of C term here, I of R plus C dVc dt. Okay. And now remember, we're trying to find our state variable, the derivative of it. And so I'm going to move everything else over to the other side. And so I'm going to get my C dV C dt is equal to I of L minus I of R. Okay. Now, what I'm going to do is I'm going to divide by C. So I'm going to get the derivative all by itself. So that's 1 over C I of L, and then minus 1 over C I of R, okay? And now, what we're going to see is, okay, this is great because I can write this as a state variable. Basically, here this would just be x1 I'm substituting in, and here is x2 dot. But what about this term I of R? That's not my input. My input is going to be the voltage here. So I need to represent this in terms of my voltage input. So what I'm going to do here is I'm going to, the current through the resistor here, how am I going to represent that? So the current going through our resistor, I can represent basically as what we're going to see here is, isn't this the voltage? They have the same voltage right here, correct? VC of T is the voltage across these two elements. It's a voltage across the capacitor, and because they're in parallel, they have the same voltage. So what I can plug in for I of R is V of C over R, right? Because that'll give me the current going through the resistor. The voltage divided by resistance gives me the current going through it. So here, what I'm going to plug in instead of I of R, I'm going to have V of C all over R. And what you're going to notice here is isn't now this only in terms of my, if I substitute in here, this is x2 dot, the derivative of VC's dVC dt. Then here, isn't this 1 over C, I of L is my x1 minus 1 over C, and then VC is my x2. So this would be just 1 over RC x2. Okay, so I wrote my state variable equation. I found the derivative of it in terms of only my states. Now, what I have to do is I have to find my x1 dot. So right here, don't you agree that the voltage in the inductor is going to be equal to the voltage from the source minus the voltage across the capacitor? And so what we're going to see here is that your voltage in your inductor is going to equal V of T minus the voltage drop across the capacitor, VC of T. And so plugging in what we have here, what we're going to notice is that the voltage in your inductor is L dit dt, correct? Is equal to V of T minus VC of T. Okay, solving now for your V of C of T, we're gonna see, let's see real quick. Is here we got x2 dot, we're gonna be solving, because we need to find the derivative of I of L, so actually divide that all over to the other side. So dit divided by dt, because we need to find the derivative. We found x2 dot, but we're trying to find x1 dot right now, is equal to 1 over L V of T minus 1 over L VC of T, okay? So now that we got that, what we're going to do is V of T is our input, we know, but VC of T, that's our x2 here. And so what we're going to have for ours is we only have it in terms of our input and our state variable. So here, if I write it in terms of our state variables, x1 dot, which is just a derivative here of our current going for the inductor, the derivative of the current going for the inductor is going to equal 1 over L. And then this is our input, 1 over L VT, because VT is the input from the source. And then minus 1 over L. And then VC of T is your x2. So we have the two state equations in terms of our state variables and our inputs. So when I go to write my matrix of my state variables, my x1 dot and my x2 dot, it's going to equal. Okay, now I need to determine my system matrix times my state variables, x1 and x2. And then it's going to be plus, and then the input vector times my input v of t. Okay. So here, what we're going to notice is looking at my x1 dot, it's 1 over L of vt. So this is 1 over L of vt. And then here it's minus 1 over L of x2. There's no contribution by x1 in the x1 dot. Now looking at x2 dot, it's 1 over C x1 minus 1 over RC x2. No contribution by the input. Now I got my state variable equation right here. I'm sorry, my state equations right here. And now I need to form my output equation. So my output equation here, it's going to be, this is going to define specifically my, let me see, VCT all over R. Let's say the output is going to be our current for the resistor. That's what we're looking at right now. So our output is the current for the resistor. So that's what we're going to try and find. So current for resistor. And we know the current for the resistor I of R, which is our output. So I of R is equal to, and then VC all over R, right? And so that's your output, the current for the resistor. And then isn't VC a state X2? So this is just 1 over R of X2. And so if you write your output equation, it's going to be the following format, where it's going to be your, X1, X2. Just pretend that one. So it would be 0 contribution by X1 and then 1 over R contribution by X2. Because we just needed to find the current through the resistor, which is given by VC all over R. These are in parallel, they have the same voltage. And VC remembers your state variable X2. And so only the contribution at the output, which is the current for the resistor, is your output, is 1 over R of X2. When you write it in terms of your output vector times your state variables, and then we have no contribution by the input signal, so that's why there's no plus d u of t. Okay, now that we have that within our equation, we're now going to look at specifically mechanical systems and how they operate. So we sort of found the electrical domain of how you operate with these types of systems. Now we need to look at the mechanical domain. So for an example, this is going to be working with forces, particularly, which is very similar to working with voltages. You know, force is just what voltage is. And so here within our diagram, we're going to have a damper. And then we're going to have a mass. And the mass is going to be mass 1. And then here we're going to have our spring, which is K. And then we're going to have another mass, mass 2. And then we're going to have our F of t here. So this is going to be F of t, so the force. And then we're going to have our displacement. So this would be x1 because displacement of mass 1. And this is going to be displacement of mass 2, represented by x2. Okay, so what we have to do is we have to define, well, here we have two masses, so we know we have two equations here within our system. Oh yeah, this is the damping, so just note D. So what I'm going to do basically here is I'm going to have to write my equations. And so notice that there's no force acting on mass 1, but there's a force acting on mass 2. So when I write my equations for mass 1, just looking at my equation 1, we need to describe all the forces on our mass 1. You know, like what are all the contributions? So mass 1, we have to look at acceleration. So mass 1, and then if we look specifically at the acceleration, we can describe that by x1, because x1's the position, how far it's moving. So x1 double dot, which means the second derivative, is going to give us the acceleration. If you take the derivative position, you get velocity. If you take the derivative velocity, you get acceleration. So mass times acceleration, that's the force we have. And then we need to look specifically at what is the contribution by the damper here. And so because we have to look at all bodies connected to our mass 1. And so the damper, it's going to be D for the damper contribution. And then remember, the damper acts on the velocity. It acts on the speed, you know, like because it's like going back and forth. So it's moving back and forth. So it's acting on the velocity. And then here we have, it's connected to the spring as well. And so the spring adjusts basically its position, so you know. So the mass is, remember, F is equal to ma, where we have the contribution due to the acceleration, then the damper contribution, because that's connected to mass 1, the spring's connected to mass 1. And an interesting part is we would have a friction force, but for this problem, we're going to assume that here it's frictionless. So we don't have to take that force into account. And then what we have to do is notice that the spring is shared by both mass 1 and mass 2. So we have to subtract the contribution by the mass 2. And then the sum of all the forces will be equal to 0 because there's no external forces acting on mass 1. And so that's why the external is equal to 0. So these are just like all the internal, because the mass times the acceleration plus the damper times the velocity plus the spring times x1. But this is connected between mass 1 and mass 2, so we have to subtract the contribution by the mass 2, and then it's equal to 0. Now, we have to write our second equation for the second body here. And so mass 2 times x2 double dot, because it's acceleration, mass times acceleration. And then here we have k x1, because this is acting on mass 2. But notice that it's shared between mass 1 and mass 2, so we have to subtract the contribution by x1. And then what we'll notice here is we do have an external force acting on our system, so F of t. So it's going to be equal to F of t. Okay, so these are our two equations of motion describing our equation. So I'm going to define, notice that we have x1 double dot and we have x2 double dot. So how many state variables are we going to have? We need 2 here and we need 2 here. So we are going to have a total of 4 state variables. So I'm going to have my Z1, my Z2, my Z3, my Z4. Z1 is going to equal X1, Z2 is going to equal X1 dot, Z3 is going to be equal X2, and Z4 is equal X2 dot. And so now, remember when you define your state variables, you have to write your state equations, which are the derivatives of those terms. So this would be X1 dot, which is just equal to Z2. Your Z2 dot will be equal to your x1 double dot. And then if you solve for your x1 double dot, you move everything over to the right-hand side, and then you divide by mass 1. And so what you're going to get is you're going to get is equal to negative d divided by mass 1. And then you're going to get your x1 dot, and then you're going to get minus k divided by mass 1. And then it's going to be x1, and then plus k divided by mass 1, and it's going to be x2. And then what we're going to have is, if you want to represent this in terms of your states, what you're going to see here is it's going to be negative r divided by m1. x1 dot is just z2. And then minus k divided by mass 1. x1 is just z1. And then plus k divided by mass 1. And then x2 is just z3. So that's how I would write my equation for Z2 double dot in terms of my states. Now, solving for Z3 dot. That's just going to be X2 dot, which is just equal to Z4. Then my Z4 dot is going to equal X2 double dot, which is equal to, move everything over to the right-hand side and divide by mass 2. What you're going to get here is you're going to get particularly K, if we move everything over to this side, you're going to get negative K, and then divided by mass 2, and then it's going to be X2, and then plus K divided by mass 2, and then X1, and then here we're going to have plus FT divided by mass 2. Now, we have to write this in terms of our states, so it's going to be negative K divided by mass 2. X2 is represented by Z3, plus k divided by m2. x1 is represented by z1. And then plus ft is our external force. That's like your input to the system. So we're going to keep that there and then divide by m2. Okay, so now I got all my state equations, basically, because when we have to write up our z1, z2, z3, and z4 dot, this is going to be equal to, then here we have our system matrix. And then we're going to have Z1, Z2, Z3, Z4, our states. And then we're going to have our input vector. And then we're going to have our input, which is f of t, the external input. And so here, remember that we're only going to see the contribution by f of t for our Z4 dot when we make our equation. And so what we're looking at is Z1 dot is equal to Z2. So it's going to be 0, no contribution by Z1, 1, and then 0, 0. 0 contribution by the input. Here, when we have to make our equation for z2 dot, we're going to notice that it's going to be negative k divided by m1. Then here we have negative r divided by m1. For z3, it's k divided by m1. And then here we have 0. And because no contribution by z4. And then we have 0 by the input vector. There's no contribution by the input, ft. Then for z3 dot, we only have a contribution by z4. Then for z4 dot, we only have contributions by z1, which is k divided by m2. Then we only have contribution by z3, so 0 for z2, negative k divided by m2. Then for no contribution by z4. Then we have our external input of 1 over m2. Okay, so now that we got that here, what we're going to specifically have is looking at our equation now. What we're going to determine here is that we need to, oh, real quick, I think, oh, did I make this an R by accident? Sorry, I meant D. So right here it's just a D, not an R. Sorry, I'm accidentally put, for it's stamping. I wrote it, I just accidentally put like a little R there. So it's actually D. Now that we have that, we need to write our output equation. And so for our output equation, what is our output for the system? And so in the mechanical system here, let's say that our output basically is, let's look, it could be the, if they told us the output is defined as, let's just say, how much is the, speed, let me see, what could we define here as our, the output is like how much it moved along x2, let's say, our body by x2. So say if like the output was equal to our x2, our position. What we would say here is that, oh, then we could describe our output as, if we had to write our output equation, so how much is the displacement x2? Notice our x2 is just by z3. So it would be 0, 0, and then 1, 0, and then have your state vector, which would be x1, x2, x3, and then z1, z2, z3, and then z4. So that would be, because your only contribution to the displacement, we have it written right here, z3. So then it would only be contributed by z3 here, if like they ask you what's the displacement. So that's what we have here. And so if they asked us like what's the output is the displacement of mass 2. And so we noticed that our state, one of our state variables was defined as the displacement. So you could just write the output in terms of that state variable. Okay, now that we define that, we're going to look at the internal dynamics of our state space so that we can understand it better because this will pop up. So remember I gave you the two formulas. X dot is equal to AX plus BU. And then we had a second formula, which was the output is equal to, here we're going to have CUT times our X, our state variable vector, plus the feed forward gain, du. And so what we're going to have is within our internal, what we're going to see here is our input, which is U, right? That's the input. So we start with the input, and it's going to go through. If we're just defining what we're seeing right now is we're going to see it. Oh, oops. Let me erase that real quick. Didn't mean to write the summing block right now. Notice that our U is acted on by B and D. And so we're going to have a block for B and we're going to have a block for D. Okay, so that's right now what we know is it's acted on by two systems, one by B and one by D. And then notice that the one attached to B is added up with the A. So there's going to be an adding block here. So we're going to have an adding block. So summation of the two. And so we're going to have a contribution by A. And then here, what's going to be at A at this point is your state vector, so X. So right now we have A of X plus B of U. So that describes our X dot here. So this will be X dot at this point right here. And then in order to get our X, right, don't you have to take the integration of it? So that's why we have a 1 over S here. In order to go from X dot and then taking the integration of it, you just get X. And then after that, we have a C times our X. So I'm going to multiply by C here. So we're going to have a C block. And then we have the summation of C of X. So C of X plus D of U. And so this is D of U right here. So this is going to add together with the two. So these two will add together and we're going to get our output Y. Okay, so that's the internal dynamics of your state space representation here. So we'll later see that come up into play. And so that was pretty much just getting a look at how state space works within our systems particularly. And now what we're going to do is we're going to look at the second part of the state space where we can go from our state space representation to the transfer function of our system. And so what we're going to see is we're used to knowing that our state space is given by the following, where we have X dot is equal to, and then if we have our system, say if we have multiple input, multiple output system, it's given by A of X plus, and then your input vector now becomes a matrix because you have multiple inputs. B of U, because you have multiple inputs, now it's a vector of inputs. And then you have Y, and then this is, because it's a multiple output system, it's a vector of Y, and then is equal to C, and then X plus D U. Because you have multiple inputs. So that's why now we have this all in terms of, this is for a multiple input, multiple output system. And we're used to working with the single input, single output system, which is just given by X dot is equal to A of X plus, and then your input vector times just one input. So that's why it's just U. And then your output equation, you have only one output, single output is equal to C of T transpose, and then your vector of states, and then plus, and then your feed forward gain DU. Okay, so that's what we're used to seeing. And so for the when we have to find our transfer function, the equivalent, what we're going to see here is that within our system, we're going to notice that for a single input, single output system, which is the only one you're going to be dealing with for this class, so don't worry about the other one, you're going to notice that your X of S is going to equal S of I minus A inverse, and then B, and then U of S plus SI minus A inverse, and then X of 0, okay? And so that's for your X of S, but for your output, Y of S, it's going to equal. Here we're going to have our C of T, and then SI minus A inverse, and then B plus D, and then U of S plus, and then C of T, and then we're going to have S of I minus A, and then inverse, and then we're going to have X of 0. So notice that this second part is just due to the initial conditions, X of 0, X of 0, but this first part is just due to your external input, U of S. And so we have the external contribution and the internal, external and internal contribution. And so make sure you have these two formulas for sure, just in case. That's where your system, it's basically just representing it in terms of the Laplace domain. So he basically just took the Laplace transform of here, and that's how we see the following equations down here. And so your transfer function for a single input, single output system is given by Y of S, which is your output over your input U of S. Remember, your input's U of S. It's not X of S. X of S is representing your states. So here, we have, it's given by C of T, and then S of I minus A inverse B plus D. Okay. So this is the transfer function of your system. So that is a very important equation for your transfer function. And this is because you literally just take the output and you divide it by the input. And then what you're going to notice here is that all the initial conditions are 0. So this part doesn't contribute, this part doesn't contribute at all. So when you do the output over input, that's how you get the following. So let's try finding the transfer function of a single input, single output system here, and let's see if we can get it. So let's look at an example. So we have our state vector, x dot is equal to 0, 1, 0, 0, 0, 1, and then -1, -2, and -3. So that's our input vector A. And then times x plus, then we have 10, 0, 0, and then it's going to be u. Now, we're going to have our output vector defined as y is equal to 1, 0, 0, and then we have our x, our state vector. So it says find the transfer function. So find g of s. Well, first, what we're going to have to do is g of s is given by the following, because notice first, what we have here is b is just the single vector, right? It's only a column vector. So we notice that's a single input and that it's a single output here, because it's just c of t. It's not given, c is not a matrix, it's just a row vector. So we can apply the definition up here for a single input, single output system. And so let's first work our way inwards and out. So let's find Si minus A. That's going to be equal to, here, if we have our S of I, the identity matrix, notice that A is a 3 by 3. So we're going to have 3 by 3 for S of I, which is just going to be S 0, 0, 0, S 0, 0, 0, S. And then minus, and then what's our A? It's going to be 0, 1, 0, 0, 0, 1, -1, -2, -3. S of I minus A. Now what we have to do here is we're going to have the following. So it's going to be S minus 0, 0 minus 1, 0 minus 0, and then we're going to have 0 minus 0, and then we're going to have S minus 0, then we're going to have 0 minus 1, then we're going to have 0 plus 1, and then we're going to have 0 plus 2, and then we're going to have S plus 3. So now we have to find Si minus A inverse, because that's just Si minus A right here. So in order to find Si minus A inverse, this is actually finding the inverse of a matrix, which we later found out how to actually solve. So we're going to apply that definition right here, just so if you get this on the exam, you actually know how to do it. So there's an important one. In order to find the determinant of a matrix, sorry, the inverse of a matrix, which we have here, it's going to be 1 over the determinant of our, I'm going to call this right now, just to make it easy, I'm just going to call it matrix B, okay? So this is just going to be B inverse. So you have to find the determinant of B, and then we're going to find the cofactors, basically, of cofactor 1, 1 of B, cofactor, and then it's going to be 1, 2 of B, cofactor 1, 3 of B, and then it's going to be cofactor, and then 2, 1 of B, cofactor 2, 2 of B, cofactor 2, 3 of B, and then for our last row, it's going to be cofactor 3, 1 of B, cofactor, and then 3, 2 of B, and then cofactor a 3, 3 of B, okay? So that's what we're going to have here for our actual inverse of the matrix we have to find. And so what we're going to have is we have to find these cofactors, and we also have to find the determinant of this matrix. And so the main thing when you have to find the determinant of a matrix is, if we're trying to find a determinant B, just solving for that alone, it's going to equal. So you start in your upper row. So we're going to just go by the rows, and we're going to go, it's going to be equal to, you start with your first one, so it's S. And then it's going to be multiplied by the cofactor at that point, which is 1, 1 of B, plus. And then moving over to the right, it's -1 times the cofactor of 1, 2 of B. And then it's going to be plus, you move over to the right, you go along one row. and then it's going to be 0 times the cofactor of 1, 3 of b. Okay, so now that I got that, we need to solve for cofactors because we have a ton of cofactors here we have to calculate. And so looking just at this one right now, if we're going to try and solve this, what we're going to see is it's of course going to be s. To calculate a cofactor, what you have to do is that -1 and then the row and the column added together. So 1 plus 1, and then it's going to be the determinant of what is not there when you do the so when you look at that specific cofactor, like 1, 1, you block out the first row in the first column. So it's going to be the determinant of these 4 terms right here. So that's s, and then 2, -1, and then s plus 3. Okay. Then, for your next one, dropping down the -1, now looking at the cofactor. The cofactor is -1 of the row plus the column. And then what is the determinant formed by when you eliminate row 1, column 2? It's 0, 1, -1, s plus 3. So 0, 1, -1, s plus 3. Then this is just 0 times whatever, so this term will cancel. And so what I get here is -1 to the power 2 is just 1. So I'm going to get s times, and then it's going to be here, we're going to get s times s plus 3, which is just going to be s squared plus 3s. And then I'm going to get minus a -2. Then here, I'm going to get a -1, and then here it's going to be -1, so that would just be +1. And then here I'm going to get 0 multiplied by this minus, so I'm going to have 0 minus a -1 times a 1 is going to be -1. So I'm going to get s to the power of 3 plus, and then I'm going to get 3s squared, then plus 2s here, because this would just be a +2. So now plus here, this would be 1, so +1. So that's my determinant of that matrix, the 3 by 3. Now, I have to get all my cofactors here in order to determine it. And so right now, in order to determine all my other cofactors within this matrix, so I already solved for cofactor 1, 1 and cofactor 1, 2. So I'm going to write those here. Cofactor 1, 1 of b is equal to what we had here is within this matrix here, it was s squared plus 3s plus 2. My cofactor of 1, 2 of b was equal to, and then here when I had that, that was -1 times, and then right here we had a +1. So that was +1, oh, because that became a positive. Okay, so that would be -1 times a +1 would be a -1. Now, we have to solve for a cofactor 1, 3. I never solved that. So that's -1, and then the row plus the column. And then when I eliminate row 1 and then column 3, I'm left with 0, s, 1, 2 is what I'm taking the determinant of. So 0, 1, s, 2. And so that's going to be here, this would be -1 power 4, which is just 1, and then 0, and then minus s. So that would just be minus s. Now, I need to find cofactor of 2, 1 of b. So that's going to be here, it's going to be -1 to the row plus the column. And then what's going to be my determinant left? Row 2, column 1, it's going to be -1, 0, 2, s plus 3. Now, solving for that, I'm going to get a -1 in front times, and then I'm going to get -s minus 3 minus 0. And so that's going to be our s plus 3. Then cofactor of 2, 2 of b is going to equal -1, and then 2 plus 2. And then it's going to be here, 2, 2. What I'm left with in my matrix, sorry, eliminate row 2, eliminate column 2. You're going to be left with s0, 1, and then s plus 3, which is going to equal. Here, you're going to get, of course, this would be to the 4, so it would be positive. So no contribution by that, and then it'd be s squared plus 3s. And then going on, you're going to get cofactor, and then this is going to be of 2, 3 of B, which is going to be -1, and then 2 plus 3, and then what you're going to get is row 2, column 3, S -1, and then 1, 2. This would be a -1 in front, and then you're going to get 2S, and then plus 1, and so it's going to be -2S minus 1. And then here, if you do cofactor a 3, 1 of B, what you're going to be left with is it's going to be -1, and then 3 plus 1, and then your determinant left, eliminating by row 3, column 1, it's -1, S, and then you're going to see 0, -1, and what you're going to get as a result, it's going to be -1 power 4 is just 1, then you're going to get 1 cofactor of 3, 2b, we're almost done, is going to be equal to -1, and then 3 plus 2. Then here, you're going to be left with eliminating row 3, column 2. You're going to be S0, 0, -1, which is going to equal -1 times, and then -s, which is just going to be equal to s. Then you're going to get cofactor of 3, 3 of b, which is going to equal -1, and then 3 plus 3, and then it's going to be determinant. It's going to be 3 and 3, which is going to just be s -1, and then 0s. And so we're going to get -1 power 6 is just 1, and then s squared. So we found all of our cofactors here. Now we need to write it in this format: 1 over the determinant, which 1 over the determinant. So now here, what we're left with is 1 over the determinant of b. So s of I minus a inverse is going to equal 1. And our determinant we calculated was s3 plus 3s squared plus 2s plus 1. And then what we're going to have here in our cofactor matrix is, starting out with cofactor 1, 1 is going to be s squared plus 3s plus 2. Our next cofactor is -1. Then our next one is -s. Then we're going to have our, down here, it's going to be s plus 3. Then we're going to have s squared plus 3s. -2s minus 1. 1. And then here we have s, and then s squared. Now that we got that, we finally found the inverse of our system. What we have to do from here is we got si minus a inverse. And so after you get that, remember your g of s is si minus a inverse, and then it's multiplied by c of t, and then b, and then plus d. And so what our c is the following, is 1, 0, 0. So what we're going to do here is you have to multiply all this out. So you're going to get the numerator divided by this. You're going to get numerator divided by this. You're going to get this divided by this. And so skipping a little math, because what we're going to see here is that s plus 3, and then we're going to have 1. Let me see real quick. This was si minus a inverse is 1 over that. Sorry, let me just double check one thing real quick. Oh. One quick thing, just to realize before you make any mistakes. Up here, I just forgot the transpose. When you have it defined, be careful. The inverse matrix is 1 over determinant cofactor. This transpose here term is really big. Don't forget it. So we found the cofactor matrix right here. And you have to take the transpose of it. So we got the cofactor matrix here. I just have to take the transpose of it. And so when we have to solve this, be careful not to mess up that transpose because it will change your system. If you have to do that, then what you're going to get here, si minus a inverse is equal to, then if we take the transpose and apply it, what we're going to have is we're going to have s squared. You switch the rows and columns, 3s plus 2. Then I'm just writing what I have down here, plus 3s squared plus 2s plus 1. And then I have s plus 3 here now. And then it's going to be s cubed plus 3s squared plus 2s plus 1. And then I'm going to have my 1 over, and then my denominator here is s3 plus 3s squared plus 2s plus 1. And then in my next one, I'm going to have the -1 and then all over, because that switched with this position right here. And so it's going to be -1 s3 plus 3s squared plus 2s plus 1. Okay, and then 2 stays the same right there, because if you flip it, it's exactly in the same position. Then s cubed plus 3s squared plus 2s plus 1. And then here, flipping the other position, what we're going to see is we're going to get our, if we have to flip this around, so flip that, it would become s all over, because then these two would flip-flop. We would get s cubed plus 3s squared plus 2s plus 1. And then down here, what we're going to get is negative s all over s3 plus 3s squared plus 2s plus 1. And then what we're going to have here is we're going to have our negative 2s minus 1. And then it's going to be s3 plus 3s squared plus 2s plus 1. Then you're going to have s squared all over, and then it's going to be s cubed plus 3s squared plus 2s plus 1. Okay, this is great. Now we got our entire si minus a inverse. So now that we got that, what's going to happen is, remember, our g of s is equal to, and then we're going to have our c of t, and then si minus a inverse, and then b plus d. Okay. So now, plugging in my c of t, what it is it's 1, 0, 0. Okay. And so now, this si minus a inverse, what we're going to see happen here, si minus a inverse, and then our b vector is just 10, 0, 0. And then our d vector is just 0, so it doesn't exist here. What we're going to notice is that we have a 3 by 3 here, and we have a 1 by 3. And so if we have a 1 by 3 and we have a 3 by 3, what we're expecting out the output is a 1 by 3. And so what we're going to notice here is that for a 1 by 3 vector, it's going to be, look that there's just a 1 here. So it's going to be, when we start out here, and then it's going to go down here and here. So the only contributions by this first term here, s squared plus 3s plus 2, all over, and then s to the power 3 plus 3s squared plus 2s plus 1. And then looking at our next term here, when we start on our next column, only the top one's going to have a contribution, and then all over s cubed plus 3s squared plus 2s plus 1. And then your final term, looking at the final column here, and then going, the only one is going to be the first one there. So 1 all over s cubed plus 3s squared plus 2s plus 1. Okay, and then this is going to be multiplied by 10, 0, 0. So remember, this is a 1 by 3. In here we have a 3 by 1. So we're expecting now at our output, it's going to be a 1 by 1. And so what we're going to have here is, notice that the only contributions by the 10, 0, 0. So 10 times this, that's what we're going to get for, you're going to notice that we're going to have 10 times s squared plus 3s plus 2. So it's going to be 10 multiplied by the s squared plus 3s plus 2, all over, and then s cubed plus 3s squared plus 2s plus 1. That's your output right here. So that is your g of s. It's equal to that. That was all the math behind cofactors and everything. So that gave you like a full-on linear algebra lesson, but it's good to know because that's something you probably will be tested on in order to find the cofactors and find the inverse of a matrix. So it's just given by this, a really important equation here, how you can find the inverse of a matrix. Remember that transpose though, because that will change your entire calculation if you forget it. And so make sure you know how to do that, just like we shown here. Now that we got that, what we're going to look is, we're going to look at like the inverse way of how you can go from a state space representation over to, from a transfer function to state space, because we saw how you go from state space to a transfer function. And so in order to go the opposite way, we sort of need to know like a little bit of the technique, the methodology, how we do that. And so what we're going to see is, I'm going to derive it for you guys, because I think it's important in terms of knowing how to do this if you're given an exam question so you know how to derive it. Um, so your g of s. Say if you're given a transfer function, y of s all over u of s, and it's given by b2s squared plus b1s plus b naught. And then it's all over s to the power 3 plus a2s squared plus a1s plus a naught. Okay. So we're given the transfer function right now, and we have to find the state space representation for it. So what I'm going to do is notice that my numerator, my denominator, the power of the denominator is greater than the power of the numerator. So if you have to derive the state space representation of this for any one, it will work. You're going to multiply this by a numerator, z of s, all over denominator, z of s. Okay? And so what we're going to do is, let's just look at the numerator equation real quick. So we're just going to look at the numerator. So this part right here has its own equation. And then if you look at denominator, so you can write two equations from this. Y of s is equal to b2s squared plus b1s plus b naught times, and then this is all by z of s. And then looking at your denominator, you can solve that one, which is just u of s is equal to, and then it's s cubed plus a2s squared plus a1 of s plus a naught c of s. Okay, so now what we have to do is we're going to have to, first let's solve our denominator, because once we find out what it is, then we can get our output for y of s. And so what's going to happen is we're going to want to solve for our u in order to get it by itself. So here, what you're going to notice is that we can represent this equation as, notice that if z of s, we're going to let z be our state vector. So here, you're going to have your z, notice this would be z, and then here it's to the power of 3, so z of t plus a2, and then this would be z to the power 2t plus a1, and then z dot of t, because there's only one integrator, s, and then plus a naught of z of t is equal to u of t. So if you just represent that in the time domain, if you take the inverse, this is the third derivative, this would be the second, and then this would be the first. And then, so you're just rewriting this in the time domain. And now, what's going to happen is, remember, we're going to have our states now here. So we're going to have our x1, our x2, and our x3, right? Because we have three states here. So we have x1, x2, x3. And so those x1 of t is going to equal z of t. x2t is going to equal z dot of t. And then we're going to have x3 of t is going to equal z double dot of t. Okay. So now we need to find x1 dot of t is going to equal. That would be x2t, right? And then we have x2 dot of t is going to equal x3 of t. Then we're going to have x3 dot of t is going to equal, that would be z triple dot of t. So moving everything over to the right-hand side, you're going to get negative a2 and then x3 of t, and then minus a1, and then that's going to be x2, and then we're going to, of t, then minus a naught, and then x1, and then plus u of t. So plus u of t. Okay, so we wrote our three state variables. We defined z of t as our first state variable, z dot of t is second, and then z double dot of t is our third. And then we found the state equations here. Now what we have to do is we're going to now plug this in. If you think about what is, now looking at the inverse Laplace of this equation, we're going to get y of t is equal to. Then here, we're going to have our b2, and then this is going to be our z double dot of t, and then plus b1 z dot of t plus b naught, b naught of z of t. Now that we have that, what we're going to do is, don't we have representations for this? So our y of t is going to equal b2 and then x3 plus b1 and then we're gonna have x2, and then plus b naught, and then x1. Okay, so now we have our output equation and we have our state variable equations, all written in terms of our states here. So what we can do now is looking at our representation is our state space representation x1 dot, x2 dot, and x3 dot is going to be equal to. And then here we're going to have our system matrix. So it's going to be here for it's only dependent upon x2. Here it's only dependent upon x3. Here it's dependent upon x1, x2, and x3. And so then x1, x2, x3, and then we have to have our input. Our input is ut, so it's going to be 0, 0, 1, and then ut. And then here for our output, y of t is going to equal, it's dependent upon x1, x2, and x3. So that is going to be our x1, x2, x3. There's no feed forward name here. So that's how we derive for any transfer function, which is given in this general format here. So numerator and denominator, any type of transfer function, even if they have the same power in the numerator as denominator, you can derive it this way, and you'll find the state space representation here. And so that's how we can go about finding the state space representation from a general transfer function. If we do this derivation, you just multiply by z of s over z of s, and then you solve it, and you have an intermediate variable represent your state in between, and then you can write your output in terms of just your states and your state equations in terms of your states, so it's all common there.
Wait, you said you can do it. You could do it the same even if they have the same power on top and bottom.
Yeah, that's what I did for 470, and I got it correct. Because you literally, all that changes here is if it has the same power in the numerator. Say if this was an s cubed here, right here, this would just be, s cubed, which would just be here. What we would see is if this was an s cubed, we would, let me check real quick, is that would be x3 dot, which we would have here, because we'd have x3 dot here defined in terms of our states. Does that make sense? So if I
Yeah,
had
yeah,
x3 dot, I would just copy this over and plug it in for it. So it'd be in terms of my states. Does that make sense?
yeah. That's good.
So if there was an s cubed here, I would literally derive it the same way, and this would just be a z to the triple dot, which would be x3 dot. So I'll just plug in everything here. So I'd have it in terms of my states. Okay.
Gotcha.
Now that we saw that, let's look at the state space representation for an example. So our state space, say if we have a g of s is equal to s squared plus 7s plus 2 all over, and then we have an s cubed plus 9s squared plus 26s plus 24. Now, if I have to find the state space representation, so find state space representation. What we have to do, notice that this follows just the format that we had above, right? Like it's the same exact thing. So it's the general format here. Even if they gave us like only to the power of s, then this b2 would just be equal 0. But here, if we need to find state space representation, we can just plug that in here. So notice that my b2 is 1, right? My b1 is 7. My b naught is 2. My A2 is 9, my A1 is 26, and my A naught is 24. Okay, so now what I have to do to find the state space representation, I'm just going to have my x1, my x2, my x3 dot, and then I'm just going to plug in. So I have 0, 1, 0, 0, 0, 1. My A naught here is going to be 24. So negative A naught is negative 24. Negative A1, negative A2. And then it's going to be x1, x2, x3. And then we're going to have plus. And then here it's 0, 0, 1, ut. And then here we have yt is equal to, and then we have b naught, which is just 2, b1, which is 7, and b2, which is 1. And then x1, x2, x3. So I just literally plugged it in from above because it's just the general format. You can plug it in just to our representation here, your coefficients to get your format. So there we go. Okay, now that we found that, you can see how if you have the general format, you can just plug in your coefficients here and get what you need. So now that we have our state space representation, let's now do, let's say, remember how we define back here, x of s and y of s. So what we had here is if we have to find x of t and y of t, say that we're given the following format where we need to solve for x of t and y of t. So writing a little subnote here. So let me write that on this piece of paper right under it. So our x of t is given by Laplace inverse, and then it's going to be s of I minus a inverse, and then b u of s, and then plus Laplace inverse, and then it's going to be s of I minus a inverse, and then the initial condition vector. So I literally, in order to find x of t from x of s, I just took the inverse Laplace and inverse Laplace. This is just capital B here. It can be, sorry, I was just using this for the multiple input, multiple output system, but applying it as single input, single output, it'd just be B and then, the vector B instead of matrix B. And so now that we have that, in order to find the Laplace inverse then of our y of t, what we have is our y of s is given by here. So in order to find y of t, it would be equal to, and then we have Laplace inverse, of course. And then if we're writing it for a multiple input, multiple output system, it would be C, so matrix C here, and then our B, and then plus D, and then we would have our U of S, and so Laplace inverse of that side, plus, and then Laplace inverse, and then it would be RC S of I minus A inverse, and then our initial condition vector. So it'd be Laplace inverse of both sides here on our y of s in order to get our yt. Now that we have that, let's say we have the system and we need to find the states and the output. So remember, this is your states, your x of t, and this is your output here. So sorry, x of t, is this is a multiple input, multiple output vector. That's why I'm using for our output, it's a vector, and for our states, we're gonna have more than one state. So let's say we're given the following system in the state space, where it's x dot is equal to 0, 1, -2, -3, then it's a vector of x plus, and then 2, 0, u. And then our y is equal to 0, 3, and then our states. Now, what we have to do here is we're going to have to find the states in the output when the initial condition vector. So find the states. So if you see find the states, remember that's your x of t, and output y of t when your initial condition vector, so x 0 is equal to 1, 0, and u of t is the unit step. So what we're going to have here is looking at our x of t. So we're given, this is your A, this is your B vector, this is your C transpose vector, correct? So let's just plug that in to find our states and our output. And so remember, this is a single input, single output system. Because notice I have a single output here, it's just C of t, and then single input. You just have a B vector. So in order to find x of t, it's going to be equal to Laplace inverse. And so here we're going to have s of I minus a inverse, and then b, and then we're going to have u of s plus Laplace inverse of si minus a inverse, and then our initial condition vector here. So I wrote this just in terms of the vector format. So you see that term as well. And then we're going to have our, because remember, this is single output system, so it's just yt. It's no longer vector, is equal to Laplace inverse. And then here it's going to be C transpose vector, and then Si minus A inverse. and then B vector plus D, and then U of S plus Laplace inverse. And then SI C of T, and then SI minus A inverse, and then X, not initial condition vector. So the main thing is if they gave you initial conditions, I would be like, oh, shoot, I need to use these equations. So what we're going to see from here is then we need to plug in what we have in order to solve. And so let's start with our states. So we're at, notice that we have S of I minus A inverse for like a lot of these. So let's first just find what that is, because we're going to have to like plug that in a bunch of places. So S of I minus A is equal to, here we'd have S minus 0. Then we would have 0 minus a negative 2, so that'd be positive 2. And then at 0 minus a negative 1. And then we would have S minus a negative 3, so S plus 3. Okay, now I need to find S of I minus A inverse. Okay, so in order to do that, in order to find determinant, it'd be 1 over the, and if I call this B, 1 over determinant of B. And then it's going to be, remember, the cofactor of 1, 1 of B, cofactor of 1, 2 of B, and then we have cofactor of 2, 1 of B, and we have cofactor 2, 2 B. And then remember, this is transpose. So in order to find that, we need to first find the determinant. Determinant, and then we're calling that B of our SI minus A is going to equal. We're going to have S times S plus 3 minus 2 times negative 1, which is going to equal S squared plus 3S, and then plus 2. Now, cofactor 1, 1 is going to be, cofactor 1, 1 of B is equal negative 1, and then row 1 plus column 1, and then we're going to have, eliminating those, it'd just be S plus 3. Then cofactor of 1, 2 is going to be a B negative 1. Row 1 plus 2 is then eliminating row 1, column 2 is going to be negative 1. And then we're going to have cofactor of 2, 1 of B is going to equal negative 1, row 2 plus column 1. And then row 2, column 1, it's going to just be 2. And then cofactor of 2, 2 of B is going to equal negative 1, then 2 plus 2. Then so 2, 2, it's just going to be S. So now that we found that, what we're going to have here is plugging in what we have. So SI minus A inverse is equal to 1 over, what's a determinant? It's S squared plus 3S plus 2. And then what we're going to have here is cofactor of 1, 1 of B is going to be, this would just be a positive 1 times S plus 3. Then we're going to have cofactor of 1, 2b, which is going to be here negative 1 times a negative 1 is just a 1. Then here this would be a negative 1, and then times 2 would be negative 2. And then here we just have 1 times s, which is just s. And then remember transpose. Now, in order to take the transpose, what we're going to have is we're going to have s plus 3, and then negative 2, and then 1, and then s. Then it's 1 all over s squared plus 3s plus 2. And what we're going to get is we're going to get s plus 3 all over s squared plus 3s plus 2. Then negative 2 all over s squared plus 3s plus 2. Then 1 over s squared plus 3s plus 2. Then we're going to get here s all over s squared plus 3s plus 2. That's our matrix. Now, what we have to do here is we found SI minus A inverse. What we have to do from that is we can plug that in here. And then we have to multiply it by B in order to get our term, and then multiply it by our then input, what we have here. And so for our system, when we have to find our x of t, what we're going to have to do is multiplying this, now SI minus A times B U of S. So I'm going to now look at that component right there. And so looking at that, what we're going to see is if I do SI minus A inverse times our B vector. That's going to be just this multiplied by 2 comma 0. So I'm just going to do that math. So 2 comma 0 multiplying that by this, it's going to be what we're going to see is that's literally just adding like a 2 0 vector here. So it would be this multiplied by 2, and then it'd be 0. So it would be 2 times s plus 3, so it'd be 2s plus 6 all over, and then we're going to get s squared plus 3s plus 2. And then for our next one, it's going to be our 2 0 vector would be here, so it'd be here and then here, and so it'd just be 2 up here. So we would get, for ours, it would be a 2 all over s squared plus 3s plus 2. Okay. So this is our SI minus A inverse of B. So we found this part. Now, what this is going to be now is just our U of T is going to be multiplied in, when we take the Laplace inverse, this would just become UT, but right now, if it's just multiplied by U of S, so if you just multiplied by U of S would be on the output here. But you also have to determine what's this multiplied by your initial state vector. So your initial state vector was 1, 0. So finding SI minus A inverse, oh, sorry, okay, I accidentally wrote that inside. And then x0 is equal to, well, this one's pretty easy because it's just 1, 0. So it's going to be this multiplied by 1, 0. Then this 1, 0. So it's just going to be s plus 3 all over s squared plus 3s plus 2. And then here it's going to be 1 all over s3 plus, sorry, s squared plus 3s plus 2. S squared plus 3s plus 2. Sorry, I'm sort of running out of room, but you know what I mean. Okay, so now that we got that, what we have to do is we found those, so we're going to plug that in for x of t. So our x of t is equal to, we're going to have Laplace inverse, and it's going to be of SI minus A of B, right? SI minus A of B, and then U of S. So SI minus A of B. And so it's going to be this, which is 2s plus 6 all over, and then we're going to have s squared plus 3s plus 2, and then all over 2 all over s squared plus 3s plus 2. And then we're going to have this multiplied by our U of S, and then we're going to have, remember, what's U of S? It's just 1 over S, right? And so, because UT is just, remember, they said the input is a unit step. So UT is just our unit step. So U of S would equal 1 over S, right? Just the Laplace transform of the unit step is 1 over S. So right here, what you can do instead is you can just substitute 1 over S in here. But then it's going to be a plus, and then Laplace inverse, and then it's going to be SI minus A inverse times your initial state vector. So here it's going to be S plus 3 all over S squared plus 3S plus 2, and then it's going to be 1 all over S squared plus 3S plus 2. And then this is going to be multiplied by, oh, that's it. And so we just have to find the Laplace inverse of this to get our state vector. And so what we're going to do here is then after this, so you would just replace this with a 1 over S, because that's just your unit step. And then so this would become 2s plus 6 all over S times S squared plus 3s plus 2. 2 over S times S squared plus 3s plus 2. So you would have to find the Laplace inverse of that. When you go to take the Laplace inverse of this, what you're going to have to do is either you can do partial fraction decomposition here in order to solve it. And then when you do the partial fraction decomposition, what you're specifically going to get is your x of t. And so you'd have to apply partial fraction decomp because this would have an s times an s squared plus 3s plus 2 in the denominator, where here you could actually then use one of, so this is where you'd have to use your Laplace table. And so make sure you have that on your sheet in order to find the inverse Laplace of it. But if you do take that, what you're going to get for your x of t vector is it's going to equal your here, what we would specifically see for ours is that we're going to have ours would be specifically solving for this. Let me see. Give me one quick second. It's going to be 2e to the negative t plus 3, and then minus e to negative t plus 1, and then u of t. Okay. And so then that's what we get here. And then for our y of t, if you have to find the output y, you would do the exact same thing. You know how to plug that in, and then you could solve for y of t because we found s of I minus a inverse b. You just do and solve for it and then take the Laplace inverse. So that's how you go about that example, working it out. Now that we talked about that, what we're going to see here is there's a special type of matrix, and sort of defined as the state transition matrix. So the state transition matrix is defined as phi of t. And it's going to be equal to Laplace inverse, and then it's going to be s of I minus a, and then inverse. So we have to take the Laplace inverse of this. And so that's going to equal e to the ta. And so what we're going to notice here is that this is our state transition matrix. So if he ever asks you for it, you literally just take the Laplace inverse of that. And so for our specific one, say if we had to find the state transition matrix of the example we just had here. So this example, if you had to find the state transition matrix, didn't we find s of I minus a inverse, which we got to be here. This was our s of I minus a inverse. And so you would have to take the inverse Laplace of that. So s of I minus a inverse we got to be the following. We got s plus 3 all over s squared plus 3s plus 2, and then negative 2 all over s squared plus 3s plus 2. And then we got 1 all over s squared plus 3s plus 2. And then we got s all over s squared plus 3s plus 2. So taking the Laplace inverse of this, what we're going to get, so Laplace inverse of s of I minus a inverse, what are you going to get? Now, notice here that what we have in our denominator is you have s plus 2 times s plus 1, right? Because that's what we have here. S plus 2 times s plus 1 gives you s squared plus 3s plus 2. So you're going to have to divide that into 2 and then use partial fraction decomposition on this in order to solve for it. So what I'm going to do is I'm going to represent this. So you would have to break this up specifically. So let's just find the Laplace inverse of this term real quick, just so you can see an example of how you would do it. So you have s plus 3, and then I'm going to rewrite that. So it's s plus 2 times s plus 1, right? And that's going to equal a over s plus 2 plus b all over s plus 1. Solving for my a and b, my a is going to equal s plus 2 times this entire thing. So then that would be s plus 3 all over s plus 2 times s plus 1. And then substituting in, what I'm going to have is s is equal to negative 2. Notice that these will cancel. So you're going to be left with negative 2 plus 3 is 1 all over negative 2 plus 1 is negative 1. So negative 1. Then your b is going to equal s plus 1 times that entire thing. So s plus 2 times s plus 1. Substituting s is equal negative 1. It's going to be equal to negative 1 plus 3 is 2. All over negative 1 plus 2 is 1. And so we're going to get 2. Okay. So here, what we're going to have is we're going to have negative 1 all over s plus 2 plus 2 all over s plus 1. Okay. So now I have to find the Laplace inverse of that because that's what we're going to apply. So looking here, having find the Laplace inverse, what we're going to get is looking at our table specifically for the Laplace transforms, we're going to get minus, so taking inverse Laplace of this, you're going to get e to the negative and then 2t here. So minus, because of minus in front, e to negative 2t. then plus 2 e to the negative t. So that's what we have here. And so this would be negative e to negative 2t plus 2 e to negative t. Okay, then you do that for all three of these right here. So then if you actually solve all that, it would be for this term up here, you're going to get 2 e to negative 2t, and then minus 2 e to negative t, and then we have negative e negative 2t, and then plus e to negative t, and then down here 2 e to negative 2t minus e to negative t. So that would be your state transition matrix. So this would be your phi of t is equal to this. Okay, so that would be your answer. You would basically go through and find the Laplace inverse of all that after you found your S of I minus A inverse. So now that we saw that, what you're going to do later on is from this, we need to learn how to linearize. So we're used to dealing with like in controls, everything's nonlinear, and then we just linearize it to get what we want. So that's what we're going to do next. So let's pause for about like 2 minutes real quick. Okay, so looking at state space linearization, if we're going to start out with that, what is it? So most practical systems aren't linear, so we're going to learn how to approximate them. And so this is called linearizations. And so we're going to like linearize it around an operating point. So it's like small changes in the of the state and input signals around your operating or equilibrium point. And so a lot of times is, remember state, we have our x. So for small changes around x, we summarize that with x naught. And this is known as our delta x. And so it's just for small changes we have around this point. And so that's what linearization is. It's basically linearizing it around small changes around that point. And so what we're going to do is we're going to try and linearize nonlinear systems. And so what you're going to notice is that if we have our h of x, so our function h of x minus h x naught. So just right here, if we take like the function of it, that's going to equal, and then if we have our derivative of h of x all over x dx, and then for x is equal to x naught, and then delta x. So this comes from our Taylor series approximation, where we represent this as our delta y. And so this is just for small changes in y. It's given by this approximation here, where we have our equation here, where it's just the derivative at that point, and then for the small changes in x, this is just x minus x naught. And so that's what we're going to see here is the general equation we have. And so let's plug in an example just to see how you linearize. This is just using Taylor series approximation. So it's a pretty close approximation we have. So I guess I should put an approximation sign. So if we had the following example, y is equal to 5 cosine of x. And they say linearize it. Notice that this is not linear because of cosine. Cosine is non-linear. You know, like it's moving up, down, up, down. It's not like a straight line. Like a linear equation would look something like this. Because it's just a straight line. If you think about it, it looks like that. Cosine's changing. And so what we have is, for this, they say linearize around the operating point. And your operating point is going to be given by x, oh, sorry, let me just write it here. X naught is equal to pi over 2. Okay, so what we have to do here is we know our y, we know what our x is. So remember our equation given up here. So what we're going to do is I'm going to write this, you can write as y minus y naught is approximately derivative of, and then right here it'd be like your y over well, if it's like your x, dy of x divided by dx. Then for x is equal to x naught, and then it's going to be x minus x naught. Just rewriting that equation in terms of my y here. So we solving for y, what's going to be approximately is y naught plus dy of x all over dx, where x is equal to x naught, and then times x minus x naught. Okay. And so my x naught here is going to be pi over 2. So here for my y naught plugging in my initial condition for my pi over 2, we're going to have y is approximately 5 cosine, and then here it's pi over 2 plus, and then the derivative of 5 cosine, and then here it'd be of x dx, then for x is equal to pi over 2, and then times x minus pi over 2. So here, what we're going to get is 5 cosine of pi over 2 is 0. And then we're going to have our derivative. So derivative of this is going to be, cosine would be negative sine. So it's going to be negative 5 sine of x, where x is equal to pi over 2. And then times x minus pi over 2. So that's what our y is approximately. Our y is going to be approximately negative 5 sine of pi over 2 would be 1. So negative 5, then times x minus pi over 2. And so what you're going to see here is this would be our format right here for your linearization around the operating point. But if you want to represent this in terms of your delta y, because remember, y naught was just 0. So if you move it over to the other side, y minus 0 is delta y. And so negative 5, and then this would be your delta x. So either of these, I believe, are acceptable for him, but that would be your linearization around the operating point. So what we're going to see here is this is probably the preferred term that he wants, so you might want to write it in this way. Let's say that y is not just like y equals 5 cosine of x. It's not just, it's like a vector of x here. It's not just one element. So if we have y is equal to h of, and then this is a vector here, what we're going to get is using our Taylor series expansion, you're going to see that y is approximately, and so we're going to have, remember how is y naught here is approximately y naught? Instead, it's going to be y and then of x naught, like an initial vector, initial condition vector of x naught, instead of just y at that one point. And then it's going to be plus, then we're going to have to take the partial derivative with respect to x. Instead of just taking the derivative with respect to x, you have to take the partial derivative with respect to x of our y of x. And then it's going to be for x is equal to, and then our initial vector column, and then the transpose of this, and then it's going to be multiplied by x minus x naught. Okay, so this is just for multiple inputs for our y. Like our y is a multiple output system, and so it's a function of multiple inputs. And so what we're going to see here, basically, when we're going to write this out is, let's look at an example where we have to linearize the system in order to get its output. And so this example follow very closely with what we're going to see here, because it will help us in order to better understand what's going to be happening within our system. And so what we're going to have is a robot has two equations that describe its motion. And so the first equation for an example is going to be x of e is equal to L1 cosine of theta 1 plus L2 cosine of theta 1 plus theta 2. The next equation describing it is going to be given by y of e is going to equal L1 sine of theta 1 plus L2, and then sine, and then it's going to be theta 1 plus theta 2. Okay, so here what we have to do is now we have to go about in order to linearize, let's say if they say linearize x of e around theta, so the initial condition for theta is equal to theta 1, 0, and then theta 2, comma 0, okay? And so what we have to do is remember, now using our equation here, so x of e is what we're going to try and linearize here. And so x of e is what we're trying to linearize, is approximately. And then here we're going to have our x of e, and then substituting in our initial condition basically for what our x of e naught is we're going to see that this would be our x of e evaluated at theta naught, correct? That would be what we have here. This would be our vector, and then plus. And then here we're going to have the partial derivative. Well, our partial derivative is going to be taken with respect to, and then here it's going to be our theta is what we're taking our derivative with respect to. And then it's going to be what are we plugging in here? And so what we're going to see is that this is going to be a function of theta 1 and theta 2, right? Function of theta 1 and theta 2. So what we're going to have here is it's going to be x of, because here you still have your y just like we had here. So just trying to keep it as simple as possible. It's x of e, and then it's going to be for your theta vector, and then it's going to be for theta is equal to your theta naught, your initial condition. So for theta equal to theta naught, so just like we had here, theta is equal to theta naught, then the transpose of this multiplied by theta minus theta naught. So you can see it matched up exactly with here. We're taking, what we notice here is that we have this is the output they want us to linearize. And so remember, you have the output is approximately the output at the initial condition plus the partial with respect to the variable. The variable here we're looking at is our theta, x of e, which is our output, and then the initial condition, the variable, which is theta, and then for the theta is equal to the initial condition, the transpose of that, and then theta minus theta naught, this vector. Okay, so everything makes sense now, just applying the definition from up here. So what we're going to do is remember that we have theta 1 and we have theta 2. So we're going to have to look at this with respect to both variables because x of e is a function of theta 1 and theta 2. And so x of e, if we pull this over to the other side, if I just minus x of e, and then theta naught here, what we're going to get is, don't you agree, if I pull this over to the other side, it's just saying the exact same thing. So here, this is going to be a vector because remember, we have theta 1 and we had theta 2 here. So we're going to have the partial with respect to theta 1 first. And so the partial with respect to theta 1 of xe, and then our theta, plus, and then our partial with respect, sorry, that would be your first element in the vector. Then your second element in the vector is the partial with respect to theta 2. So that's going to be xe, and then this is going to be of your theta, so with respect to theta 2. And then now that we have that, what we're going to have to do is you're going to have to evaluate that at theta is equal to your initial condition vector theta. Then you take the transpose and then theta minus theta naught, okay? So right now we have that. And so what I'm going to do here is what we're going to see is taking the partial of this with respect to theta 1. What are you going to get? So here, remember, if you take the derivative with respect to theta 1, it's going to be L1 times sine, negative L1 sine of theta 1, right? And so what we're going to see here is this is going to be approximately, so I'm going to just substitute this with my delta XE, okay? So my delta XE is going to be approximately, and then here, taking the derivative of this up here with respect to theta 1, what you're going to get is negative L1, and then sine of theta 1. Then here, you're going to have your negative L2 sine, and then it's going to be a theta 1 plus theta 2. And then we're going to see here, we're going to have negative, taking the respect with theta 2, you're going to get negative L2, and then sine of theta 1 plus theta 2. Okay, so that's for your theta right now, because it's a function of multiple variables. And so that was just taking the partial derivative of both of those from this term up here. And so now we're going to have to plug in for theta is equal to theta naught. And then the transpose of this, and then theta minus theta naught, okay? So I just took the partial, so I just did the partial. And now what we're going to have to do is plug in for theta is equal to theta naught. And so looking at these in particular, what we're going to get, and then this is for small perturbations around it, you're going to get, it's approximately negative L1 and then sine, and then plugging in here, what we're going to see is for this one, for theta 1, it's going to be for theta of 1 comma 0 for that initial condition minus L2 sine, and then this is going to be for theta 1 comma 0 plus theta 2 comma 0 for that initial condition. Then here we're going to have negative L2 sine, and then it's going to be theta 1 comma 0 plus, and then theta 2 comma 0. So that's just plugging in our initial condition here. And then what we're going to have is going from that, we're going to have our oh, sorry, because this is a row vector. This is going to be our column vector of theta minus theta 1 minus theta 1, 0. For the small perturbations, theta 2 minus theta 2, 0. Okay? Is that's your vector right here. This is a vector of theta 1 minus theta 1 comma 0, and then here theta 2 minus theta 2, 0. So corresponding with those theta values, and then we just plugged in here for our theta. This is because we're looking specifically at our theta 1, 0, theta 1, 0, theta 2, 0, theta 1, 0, theta 2, 0. Okay, so this is what we have for a linearized form of our equation. So what they like to do is they like to simplify the argument, and he just likes to say, instead of here, he replaces this vector right here with a partial with respect to theta 1 and partial, for small deviations around theta 1 and for small deviations around theta 2. So what we did is we just used this generalized formula here. And we literally just wrote it for R. So we started with our x of e, which was our output, and then that's approximately equal x of e evaluated at that initial point, plus the partial with respect to x of e at theta is equal to theta naught. So because we have multiple inputs, then theta minus theta naught. And then here we linearized it, and so we just substituted in here for x of e minus x of e theta naught, just with delta x of e, which is for your small changes on your output. And then this is the small changes in the input, right? So that's why at the end we just say for small changes in theta 1, for small changes in theta 2. You have to take the partial with respect to each variable. And so we had two variables. That's why we have two elements within our vector. And then you plug in, because this is theta 1 at theta 1, 0. So here for theta 1 is theta 1, 0. And this is then for theta 1, 0. For theta 2 is theta 2, 0. And so that's what you do here in order to get your linearized equation around your operating point. Okay, so now that we got that, what we have to do is basically within our system, there's a special type of matrix, which is known as the Jacobian matrix. Honestly, I don't think we need to know that. I think we're good. Let me see. Unless we'll do one more example with linearization, but I don't believe we never seen it in practice, the Jacobian, so I don't think you guys need to be worried about that one. But let's say that we have to find a state space representation. So if we're given another example, so that was just finding our linearization, but what if we're given the following equation? J, then d squared theta dt squared plus mgl divided by 2 sine of theta is equal to capital T. And so what if we need to find the linearization of this equation to find like this we need to find the nonlinear, then we need to find the linearized system. So this is around the equilibrium point, theta is equal to 0. And so the state variables, if you were given this, what you would do is, oh yeah, and we need to find our state variables from this equation. So dividing everything by j, because our state variable is going to be theta, because that's what the derivative term is of our matrix. You're going to get d squared theta divided by dt squared. And then now what we have to do here is remember how we like to write our differential equations is we like to move everything over to the other side. So minus mgl all over 2j sine of theta, and then plus t all over j. Okay, so this is what we're going to have here. And so now having my state variables, x1 is equal to theta, x2 is equal to theta dot, and then we're going to have x1 dot is equal to x2, and then x2 dot is going to be equal to, and then here it's going to be negative mgl all over 2j, then sine of x1 plus, and then 1 over j, and then t, which t is going to be your applied torque. So that's going to be your input. So here, what we're going to see for state space representation is then if we were to make our state variables, we would see that we would specifically have x1 dot or x2 dot, and then is equal to, and then here we would have our vector 0, 1, and then it would be, for this one, it would become our negative, trying to think how we would linearize this one. Notice that this is non-linear here. That's the issue, is how do you write this inside a vector for your state variables? And so the important thing to notice here is what we have to do is we have to linearize this. So in order to linearize this, what we're going to see is from here, we're going to specifically take our, what we're going to do is taking, we just learned the equation here, is basically we're going to have our x2 dot minus and then like x2 for small little perturbations around. So looking at our specifics, if you move this over to the other side, you're going to have your delta y, right? And so here we're just going to have our delta, and then x2 dot is going to be equal to, moving this over to our side, that's how I got my delta x2. So we have to take the partial now. So taking the partial of this with respect to, so taking the partial with respect to our x1, what we're going to see here is that this is negative mgl over 2j, and then a sine x1, and then evaluating it specifically at x1, because this is for small distances around 0 and x2 is equal to 0. And then remember you have your delta x1 term here. And then what we're also going to see is because this is a function, if we're trying to look at, is there delta x1 plus delta x2 plus 1 over j. So this would be for delta x1, taking the partial of this with respect to. Okay, real quick. Let's look at we're trying to make our equations here. And so we got it all the way up to this point, but we have an issue because this one is not linear. It's a function of a non-linear. So we need to write the matrix, but we're having some issues. So if we look at delta x1 dot, it's going to be equal to, okay, noticing that we have 0, x1 plus, and then we have 1, x2, and then we have none of our inputs, so 0t. But then when we have to take our delta x2 dot, it's going to be equal to negative mgl all over 2j. And then when you take the partial, that you get cosine of x1 is taking the partial with respect to x1 in this equation. And then what we're going to notice is x1 is going to equal 0 and x2 is going to be equal 0 because we're operating around that point. And then for delta x1, then we have to do plus, and then what we're going to see here is we have no contribution by our x2 at all in this one. So what we're going to have is 0 for that. And then what about our contribution by t, the input variable? Well, we have 1 over j. So when you're going to take the partial with respect to t here, you're going to get 1 over j. And then what's going to happen is plugging in that point for x1 is equal to 0 and x2 is equal to 0. That's not going to plug in anywhere. And then it's for your small deviations around t. And so what we're going to get here within our matrix, now we had to form partials because we couldn't represent this one in terms because it was a nonlinear. What you have is you have delta x1 dot and then delta x2 dot is equal to, and then here we have a 0, negative mgl all over 2j because cosine of 0 is just 1, and then times delta x1. And then what we're going to see here, 0, 1. And so this is our delta x1 or delta x2. And then it's going to be 0 and then 1 over j. And then for input of t. Okay. So what we did is we basically just had our y minus y of x naught. So that is where we have like our delta x1. You take the partial with respect to each variable. So the partial this with respect to x1 is just 0. The partial this with respect to x2 is 1. And the partial with respect to t is 0. Then here, take the partial this with respect to x1. You get this cosine of x1. Remember, you're operating around the origin. And then times the small deviations in x1 plus 0 because there's no x2 term in here. Taking partial with respect to t, you're going to get, for here, what you're going to notice is it's going to be 1 over j, and then plugging in 0 for x1, 0 for x2. Doesn't plug anywhere, but it's for small deviations around t. And so here, what we're going to get is we get our equation in this format for our state variables. And so this is the linearized system. Oh, sorry, I forgot delta t here because it's the partial of our input. So that's the output equation. So in summary, the nonlinear system, you just basically have your output minus your output at that initial condition. And then what's going to happen is that becomes your delta of your output is equal. And then you take the partial with respect to that variable, partial with respect to that variable, and you plug in. Hey, Jason. I'm just trying to take her on a walk. Okay. Then you plug in your variables around that operating point, then multiplied by, and then that small deviation in that variable. And so that's what we see for the nonlinear systems, try and linearize it. So that's how we got our output here, if that makes sense. So hopefully that makes sense a little more with the nonlinear and trying to linearize. I think you might see one example, but I feel like the example might be more familiar with this one because I remember that in 370, there was one that looked like this on his equations. So now that we talked about that, what we need to do after nonlinearization is we're going to jump in now to our state feedback and looking at how state feedback systems work in particular, because they're used in a lot of our systems. And so for the state feedback one, let me see, do I have the proper? Okay. The state space feedback, give me 1 sec real quick. Let me, so for state space feedback design, what we have within this is, this one is a little more linear algebra, which we sort of just saw already today. And so the determinant of a matrix. Say if you're given the matrix A is equal to A, C, B, D. You're used to finding the determinant, and that one's pretty easy. That's just equal to AD minus BC. Okay? And so that's pretty chill. And when you have though an n by n matrix, so say, what if your matrix is given as B is equal to, and then you have A, B, C, D, E, F, and then G, H, I. Well, if you have to find the determinant of B. And so what we saw today, in order to find the determinant, what you do is you basically start with your row. So you start at the top row and you just make your way to the right. And so what we would do is you'd have A and then times the cofactor of 1, 1 of B, and then plus B, you move to the next one, and then you have the cofactor of 1, 2, and then B, then plus, and then C, and then you have the cofactor of 1, 3 of B. And so then evaluating your cofactors, what you're going to get is you're going to get -1 and then row plus column. And then if you eliminate the first row, the first column, you're left with EFHI, which is the determinant you take, EFHI. And then for next one, you would do plus B -1 and then row 1 plus column 2. And then row 1, column 2, you're left with DFGI. So DFGI and then plus C, cofactor 1, 3, row 1, column 3, DEGH. So -1, 1 plus 3, DEGH. And so that's what you're left with. So that's how you find the determinant of like any n by n matrix, you can find the determinant. And so now we need to talk about linear combination. So if we have a linear combination, what that means is basically, so now we're talking about linear combination. What is that? Okay, so that basically means if I have a constant in front of my vector, so plus alpha 2 v2, then plus dot 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 plus alpha k vk. This is a linear combination of your vectors because it's linear. It's just a constant multiplied by vector plus a constant multiplied by vector. So literally you're adding them together and it's just multiplying by constant coefficient in front. And so what we're going to see is vectors are linear independent if 0 is the only solution. Another way of putting this is that the determinant of A is not equal to 0. So the determinant of your matrix is not equal to 0. That is if they're linear independent. 0 is the only solution and the determinant A is not equal 0. So what we're going to see here is this would be held if alpha 1 is equal to alpha 2, which is equal to, and then alpha k, all of them must be 0 in order for alpha 1 times v1 plus alpha 2, v2 plus dot dot dot, alpha k, vk is equal to a column of zeros. Okay, so in order for them to be linear independent, the only solution is that all the coefficients must be 0 in order for this equation to hold true. Otherwise, they're linearly dependent upon one another. So it just means that all of them must go in different directions. The only possible solution is if all the coefficients are 0, then it's 0. So looking at the following, we're going to look at a few examples. So v1 is equal to 2, -1. Then we have v2 is equal to 1, 0. And so what we're going to get here is we're going to have alpha 1 v1 plus alpha 2 v2. And we're going to see if that is equal to a column of 0. For what values of alpha 1 and alpha 2 can we get a column of zeros? So if we can find any coefficients that make it equal to 0 other than 0 for alpha 1 and alpha 2, then it is not linear independent. So what we're going to see is alpha 1 times 2, -1, plus, and then alpha 2, and then we're going to have here, it's going to be 1, 0. is equal to the column of zeros. Now, what we're going to see here is that writing your system of equations, alpha 1 plus, so 2 alpha 1 plus alpha 2 is going to be equal to 0, and then negative alpha 1 plus, and then this is no alpha 2, so this one's just equal to 0. Sorry. Because there's a 0 contribution by alpha 2. So what we're going to see here is just alpha 1 is equal to 0, right? From this equation here. And then if we have 0 plus alpha 2 is equal to 0, then alpha 2 must be equal to 0, right? So alpha 1 must be equal to 0, alpha 2 is equal to 0. And so that's the only solution that works for a system of equations. And so what we're going to say is that because alpha 1 is equal to 0 and alpha 2 is equal to 0, alpha 1 is equal to alpha 2, which is equal to 0. Therefore, they are linear independent. And so therefore we can say linear independent or a solution. And what you can also notice is they travel in different directions. One goes 2, -1, and one goes 1, 0. So if you plot these two, you'll notice V1 goes 2, -1. So it goes down this direction, V1, where V2 goes 1, 0. So V2 they're heading in different directions, so they're not dependent upon one another. Okay, let's look at the next one where we look at our case of linear dependency. So if we have V1 is equal to, for this example, and it's going to be 2, 0. And then for next one, it's going to be V2 is equal to 1, 0. So what we have to realize from this one is, are they linear dependent or not? So alpha 1 and then times 0, 2, 0 plus alpha 2 and then 1, 0 is equal to a vector of zeros. Writing your two systems of equations, you're going to get 2 alpha 1 plus alpha 2 is equal to 0. And then you're going to get alpha 2 is equal to 0. And so what we're going to see here is that alpha 2 is equal to 0, right? And so what we have from these system of equations, oh wait, sorry. This is just 0 is equal to 0, right? Because 0, 0, 0. So this is, if 0 is equal to 0, that means infinite solutions. So infinite solutions. So that means you could have like alpha 1 is equal to 1, alpha 2 is equal to -2. So 2 plus -2 would equal 0. So that means like you have infinite solutions here because of this equation. 0 is equal to 0 because 0 alpha 1 plus 0 alpha 2 is equal to 0. So 0 is equal to 0. So you have infinite solutions. So they are linear dependent. You can choose any values for alpha 1 and alpha 2, and then it's going to be satisfied. So they are not linear independent because they have more than one solution. And now that we've seen that, what we have to do is, within ours, there's a special thing called the rank of a matrix. And so we need to know what the rank of a matrix means. So the rank of a matrix is the maximum number of independent columns in the matrix. So rank of the matrix equals number of independent columns and columns in that matrix. Okay, so what that means is that let's say that if we have an n by n matrix, and so what we're going to see, so if we have an n by n matrix, then the rank of A must be equal to, sorry, the minimum of n comma n. So that means like if it's a 2 by 3 matrix, the minimum is 2. So then A is full rank. So when you say full rank, what does that mean? It means that basically it's linear independent. Where if we have the rank of A is less than the minimum of n comma m, then A is rank deficient. So that means it's linear dependent. So if it's rank deficient, it's linear dependent. It's also known as degenerate, that case. And so if it's though a square matrix, if we have an n by n matrix, then so this would be like a 2 by 2, 3 by 3. The rank of A is equal to n, then the determinant of A is not equal to 0. And so we say full rank or non-singular. Linear independent is another way you can say that, because the determinant's not equal to 0. But if, sorry, let me make that better. If the rank of A is less than n, then the determinant of A is equal to 0. And so that's known as singular or degenerate. Okay. So what we have here is we sort of have to look at a few matrices and determine their ranks. And so this is like a good cover of like what is a rank. So maybe like you want this on in terms of like cheat sheet, so you know if he asks you to determine if what it is. But let's look at the following. So for example, if he says what is the rank of the following matrix? So determine the rank. Matrix rank. So we see the following matrix, which is A is equal to, and then we're going to have 2, 1, 0, -1, 3, 7. Then we're going to have 0, 4, 8. So in order to determine the rank of this matrix, what we're going to have to do is notice that this is an n by n matrix. So we need to find the determinant of this matrix. So in order to find the determinant of the matrix, remember, we have the case where you just do 2 multiplied by the cofactor, and then it's going to be of 1, 1 of A plus 1, and then the cofactor of 1, 2 of A plus 0, and then the cofactor of 1, 3A. So that would be how you find the determinant of A. So determinant of A is going to be equal to that. And so what we're going to see is the cofactor 1, 1, that'd be 3, 7, 4, 8 is our determinant. So 2 times -1, 1 plus 1, and then it's going to be 3, 7, 4, 8, and then plus, and then we're going to have 1 here, -1, 1 plus 2. Cofactor of row 1, column 2 is -1, 7, 0, 8. And then we'd have 0. So here, this is going to be within our system. We're going to have 2 times, then this is 1 here, then it'd be 24 minus 28, which would be -4. Then here we have -1, and then times -8. So here we have -8 plus 8, which is 0. So determinant's equal to 0. So what we see here is our determinant, which this is also their representation for determinant. It's equal to 0. So this is going to be a singular degenerate matrix. And so that's what we see here. So this is a singular or degenerate, because the determinant's equal to 0, as we see up here, meaning that it's linear dependent. Now, let's look at another example where we have to determine the rank of that matrix. And so what we have here is we have A is equal to, and then we have 0, 1, 0, 0, 0, 1, and then we have A1, A2, A3. So we have to find determinant of the matrix. So determinant of A is going to be equal to, looking at this, what we have here is we're going to have, starting with the first one, remember how you can also go down the column way. You don't need to go down the first row. You can go down the first column as well. And so then this would be 0 times your cofactor of 1, 1 of A, plus 0 times the cofactor of 2, 1 of A, and then plus A1, and then the cofactor of 3, 1 of A. Okay, so this would be, of course, 0, 0, and then you have A1, and then row 3, and then column 1 is just 1, 0, 0, 1. And that's just going to be A1. So that's going to be your determinant. So if A1 is not equal to 0, then the determinant is not 0. So then it would be full rank. But if A1 is equal to 0, then it's going to be rank deficient. So singular or degenerate. And so that's what we have here. And so that is just going back from our definitions. So we just went by the column because it's easier. There's more zeros in the first column than in the rows. So that's what we have here. Now that we saw that, we need to look at the inverse matrix. And so what is an inverse matrix? So that was just our solution to this one. So an inverse matrix, it sort of means that what happens is if we have B A is equal to A B, which is equal to the identity matrix. So we would say that B is the inverse of A. That's what we have here. And also A is the inverse of B. So you can say that B is equal to A inverse, or you can say A is equal to B inverse here. Either one is correct. And so what we have here is that we're going to have an n by n matrix, of course. So what we're going to notice is that we can say the following. If you say A is invertible, so A is invertible. What that means is that if it is invertible, that means it's full rank. And so the columns of A are linear independent. And the rows of A are linear independent. And the same thing, because it's linear independent, we know that the determinant of A must not be equal to 0. And so those are all equivalent statements when we talk about this. And so now what we're going to see is that if you need to find the matrix inverse, so say if you need to find A1 inverse, remember we talked about this earlier where it's 1 over the determinant times your cofactors, 1, 1 of A, and then cofactor of like 1, 2 of A, and then it keeps going on and on and on. And then you have cofactor 2, 1 of A, cofactor 2, 2 of A, and then etc. It keeps going on, keeps going down, down. And so then you have to take the transpose. Remember that when you have to find. So this is finding the inverse of the matrix, which we worked with earlier in this session. Okay, so now that we know that, we're going to talk a little bit about eigenvalues. So a lot of times within these matrix inverse, of course, A and B are both the same size, right? They're an n by n matrix. So n by n and an n by n matrix. Because for matrix multiplication to work and to get the inverse, it must be. So we have eigenvalues now. So what are eigenvalues? Eigenvalues basically are the characteristic, they're roots of the characteristic of the eigenvalues of A. And so what we have is oftentimes is if we have matrix A, then the characteristic polynomial is usually given by delta lambda is equal to the determinant of delta, and then we have our identity matrix minus A. And our eigenvalues are the roots of that characteristic equation. So this is the characteristic polynomial of A right here. So characteristic polynomial of A, and the roots of those are known as our eigenvalues. So when it's equal to 0. So that's our eigenvalues. So now, eigenvectors basically are associated with an eigenvalue. And so eigenvectors, what we're going to see here is, what are they? So eigenvectors are going to be given by matrix A, and then vector V is equal to, and then lambda, and then vector V. And so what we're going to see, when vector V is not equal to 0, then it's called an eigenvector. And so let's look at an example here. So this defines an eigenvalue when the characteristics of when the characteristic polynomial of A is equal to 0 and your eigenvector is defined by the following equation. So let's look at an example here where we have our specifics. So it's going to give us A is equal to the following: 4, 2, -5, -3. And they say find the characteristic polynomial. So for this example, find the characteristic polynomial the eigenvalues in the eigenvectors. So what we're going to do here is, remember, the characteristic polynomial is given by the determinant of S of I minus A. And that's your delta lambda here is equal to that. And so is equal to, oh, sorry, this is because we're talking now about, instead of S, we're in terms of lambda. So sorry, lambda, I minus A. So this is equal to, we have to find determinant of this matrix. Well, it's easy because it's 2 by 2, so I'm literally just going to do the simple one here. So if we have our determinant, and then what we have within here is we have delta, and then this would be delta minus A, so here -4, and then there'd be 0 minus a -5, so that'd be 5. Then here it's 0 minus a 2, and then here would be delta minus a -3, so +3. And so that's what we'd get. So for a determinant of this, and so finding determinant, we'd have delta minus 4 times, lambda +3 minus 5 times -2. That would be lambda squared, and then it'd be, yeah, minus lambda, and then -12, and then +10. So here we're going to have lambda squared minus lambda, and then -2. So that is going to be our characteristic polynomial right here. So that's our solution for the characteristic polynomial. And then the eigenvalues, remember, those are when the roots of the characteristic polynomial, so for eigenvalues, those are the roots of the characteristic polynomial here. So it'll be here when it's equal to 0. So that's going to be making your equations. You're going to factor out, if you can separate this into 2. So lambda -2 and lambda +1 is going to be equal to 0. So one of your solutions is going to be lambda's equal to 2, and the other one's going to be lambda's equal to -1. So 1 in your other solutions given by the following. Now that we have that, what we're going to get for eigenvectors. So your eigenvectors are going to be A of V is equal to lambda of V. Okay. And so your A is going to be given by 4, 2, -5, 3. And then this is going to be right here. Remember, this is a vector values. V1 and V2 is going to be equal to, and then your lambda. Right here, you're going to look at one of your solutions. So we're going to look at lambda 1 in particular. So we're going to have 2 and then times V1, V2 here. Okay. So now what you have to do is what you can do, because now we're dealing with vectors, of course. So you want to make sure you're careful. what you can actually do to make this simpler on yourself is, okay, would you agree with me that you could do lambda and then times by the identity matrix minus A. So is going to be times V is going to equal 0. So if you subtract this over to the other side, you would get A times your vector V minus lambda vector V is equal to 0. So taking out the V term from both, you would get lambda, and then because you're having subtract a matrix, you multiply it by the identity matrix. So lambda, and then it's going to be identity matrix minus A is going to be equal to, multiplied by your V vector is equal to 0. So now what we're going to see here is plugging in one of your solutions for lambda. So we're going to plug in specifically lambda 1 for this one. So we're going to see within ours, we're going to get, so looking at our first solution to this equation, lambda now is going to be 2. So 2 minus A, because here it would just be 2 and then minus, and then what's your A? It's going to be given by 4, 2, -5, and then -3, and then V1, V2. So this would just be, right now, we're just going to have this as our V1 vector because it's going to be our first solution here. So you can just represent this with your V1 because we're just looking at lambda 1, your V1 vector. And so what you're going to get here is you're going to have 2 minus 4, which is going to be your -2, and then you're going to get -5. So here you get -2, and then you're going to get +5, then you're going to get 0 minus 2, so -2, then you're going to get 2 minus -3, so you get +5. And then V1 is equal to 0. And then this would be a vector of zeros, of course, because if you're going to then actually move this over, what you're going to see is that in order to go from this step here to move this over to the right-hand side, you got to remember that this is going to be your, let me see real quick. If we have to find this times this is equal to your 0, multiplying this over, you're going to see that what value would satisfy V1 here. So that's what you're going to have to realize is solving for this. Your value that's going to satisfy V1 is if this is going to be -2, and then it's going to be plus whatever is going to give you 0 here. And so what we're going to see, okay, give me a sec real quick because this was correct. -1, so here we just plugged in 2. So 2, 0, 0, 2 minus, okay, so our V1 here, it would have to be then -2 times what would give you a 0. And so -2 times, so sorry, this is really bad how I'm saying it. We have to find what values of V1 would make this 0. So -2 times our variable plus 5 times the same variable would give us 0. So because this is just a vector V1, what you can represent this as is -2 and then 5, -2 and then 5. Then this would just be V1, V1, and then is equal to our 0 vector. And so -2 times V1 plus something, so -2 times that variable, and then plus 5 times that variable is going to give you 0. And so what we're going to have here is V1, I'm going to say V1, 1, V1, 2. So if this was 2 to get 5, if you do 5 divided by 2, this would have to be 2.5. And so -2 times 2.5 plus 5 times 1 would give you 0. And so V1, 1 was equal to 2.5, and then V1, 2 was equal to 1. That would give you the solution. So if you have your V1, 1 and your V1, 2 is equal to 2.5 and then 1. So plugging in 2.5 and 1 here, you're going to get your answer of your vector zeros. And so that would be one way. vector 1, -1, never mind, this one is wrong. -1, comma 1. Wait, Fernando, am I right, or did I do something wrong here?
Oh no, you're good. It was just
Oh,
an
okay.
idea, but it was wrong.
So what you have to do is you have to find your v11 in your v12 such that this and this, because you have to get it as a column of vectors. Here, if you want to represent this, you have to find a solution for v1, comma 1 and v1, comma 2. That's going to give you your your zeros here on the right-hand side. So then it has to work for this one as well. So -2 times 2.5 plus 5 times 1 is going to give you 0 here. So that's one eigenvector because it's for when your lambda 1 is equal to 2. Now finding your other eigenvector, so we're going to look at the other eigenvector solution because we had two eigenvalues. So this one up here was for lambda 1 is equal to 2. This one's going to be for lambda 2 is equal to -1. And so then remember, we start with our A of V is equal to lambda V. Okay, so from here, what we're going to do is we're going to pull it over to the other side. So we're going to have our lambda, and then it's going to be of I minus A times our vector V is equal to 0. Okay, so from here, what you're going to notice is that plugging in your lambda to equal to -1, so -1, and then that's multiplied by the identity matrix, minus, and then your A is going to be 4, 2, -5, -3 is equal to, and then remember, this is your column of zeros. So here it is going to be 0, 0. Okay. And so this is, oh, multiplied by your V vector. Sorry, forgot to include that in here. There we go. Okay, multiplied by your V vector. So for this solution, because we're looking at lambda 2, I'm going to have this as my V2 vector, my V2 vector here. So V2, comma 1, V2, comma 2 is equal to my 0 vector. Okay, so now solving for this, -1 minus 4 is going to be -5. Then 0 minus 2 is -2. Then 0 minus -5 is +5. Then -1 minus, then here, -3 is going to give me -1 plus 3, which is going to be positive 2. And then I have v2, comma 1, v2, comma 2 is equal to 0, 0. Okay, so what value v1, 2, comma 1 and what value v2, comma 2 is going to give me this column of zeros. So -5 multiplied by 1 and then times 5 multiplied by 1 gives me 0. -2 by 1 plus 2 times 1 is going to give me 0. So I found for v2, comma 1 and for when this is equal to 1 and when v2, comma 2 is equal to 1, it works. So my v2 vector is going to equal 1, 1. And that would give me the solution here for my equation for that specific eigenvalue of lambda 2. So for this one, I found that my v1 had to be equal to 2.5, comma 1. So we found our eigenvectors, which were the values for our eigenvectors were the vectors that made our eigenvalues true to handle that equation. So we had to use this equation for our eigenvector, subtract this over to the other side, and then it'd be equal to our 0 column vector, and find the values for our v vector such that it would hold true here. So for our specific eigenvalue, we found the eigenvector that holds true for the statement. Okay, now that we saw that, what we're going to do is we're going to have to look at state space representation and how it's going to impact our systems. And so what we're going to notice specifically is that we've seen a lot of our state space representation. So remember when we started out with our transfer function, the transfer function was given by the following. G of S is equal to, and then we had C of T, and then it was S of I minus A inverse, and then B plus D, okay? And so for ours, what you're going to notice is that this is still C of T, but remember, an inverse matrix is just given by if you take all the cofactors of S of I minus A and then take the transpose of that, minus A, and then you'd find the determinant of that matrix. So then that would be the determinant of S of I minus A. Please remember, it's just the matrix, the cofactors divide by the determinant. That's what this is trying to say. And then B plus D. So that's how you'd find the transfer function. And so what you're going to notice here is that, remember how your transfer function, the poles of your transfer function, aren't they given by this right here? The poles of our transfer function are given by this determinant term, because this is what our transfer function is. G of S. So the eigenvalues, remember, because our eigenvalues are the values for which the determinant of lambda I minus A is equal to 0. So the eigenvalues are the poles of your transfer function, or also known as the poles of the characteristic equation, because the denominator of your transfer function is known as the characteristic equation, or the poles of the characteristic equation. So that is very important to know. That's why we're interested in our eigenvalues, because they're the poles of our transfer function. So that is an important note right here. So what we're going to do is, looking at this, what we're going to see is that we need to learn two definitions: controllability and observability. And so let's start out with those two. So real quick, this is why we're interested in eigenvalues for our applications. And so now let's look a little bit into our controllability and observability matrices. Okay. Controllability. Controllability is basically a system, so a linear system is controllable if, for an initial state, so this is given by x of t naught is equal to x naught, there exists an input. So this would be your state variable at an initial state. There exists an input, ut, that transfers the system from that initial state, so x naught, to the origin in finite time. Okay, so what we're going to see is we define, this basically tells us that it's controllable if your initial state, so say if we're like right here, our initial state x naught at this point, we can go to the origin in a finite amount of time. So remember, like with our systems, we might start initially at like 20 or something, but we'll return to 0. And, like after a while, like it goes down to 0. So a controllability is just basically we can transfer the system from its initial state to the origin in a finite amount of time. And so what we're going to have here is there's a controllability matrix. Given by P of C. And so what we see, I'm just going to define the one for the single input, single output system because we see that way more often. It's given by B, AB, and then all the way up to A and minus 1 of B. So B is our vector. And so the amounts for our controllability matrix is this is your number state variables minus 1. That's how much you go up to. So your n represents the number state variables. So say if I have 3 state variables, 3 minus 1 would be a to the power 2. So that's just the number of state variables you have. or you can say the order of your differential equation, whichever one. Same thing. So what we're going to see here is that within our system, we're going to notice that it's only the controllability matrix is only dependent upon A and B. C and D don't have a role within this. And so what we're going to see is that it's controllable if the determinant of PC is not equal to 0. So determinant of PC is not equal to 0, meaning that all the columns in rows are linear independent of each other. And so that's why they're not dependent upon one another. You can control any specific value within that matrix if that makes sense. And so what we're going to do is we have to determine the controllability of a system. So let's we're going to apply this to an example here. So let me see if there's a better one. I don't like the one we have in here. Yeah, I think this one's good. So let's look at the following example. So we have x dot is equal to 1, 3, 3, 1, and then x plus 1, 0, u. And then we have our output equation y is equal to 1, 2, and then of x. So it says determine the controllability. So determine the controllability. So what we have to do here is we have to form our controllability matrix. And so what we're going to see here is our P of C is going to equal, and so remember it's B. So B is 1, 0. Then it's A times B. So A times B is going to be here, 1 times 1 plus 3 times 0. So it's just going to be 1, right? And then our next one is going to be 3 times 1, which is 3 plus, and then 1 times 0 is 0. So it's just going to be 3. And then watch, because I only had 2 state variables, right? 1, 2, I only had 2 rows. 2 minus 1, it's a to the power of 1 times b. So my controllability matrix is only b, a, b. And so that's what I have here, b, a, b, okay? So this, now we have to find the determinant. The determinant of PC is going to equal 3 minus 0 is just 3. So therefore, it is controllable. I should probably say up here, it's controllable if determinant of PC is not equal to 0. So that's your big definition here. Your controllability matrix is defined by the following equation. So this is a controllable matrix. Good job. Okay. Now that we've seen that, what we're going to do next is we're going to determine for our system what is observability, because that's also something that's very important. If we can control it, that's great, but we need to observe our states. Say, what if we can't see what's happening within our states? We're going to use observability. So for observability, what we have to do is, if you only know the output and like the input to your system, that's what we're going to be focusing on. So let's see this one. So for observability, what we're going to have is a system is observable if you can determine the initial state of the system through measurements of the output and input. So a linear system is observable if you can determine the initial state of the system. So that'd be x of t naught through measurements of the output and the input. So you're measuring in between the output and the input and sort of trying to guess, like what is your state. And so what you're going to notice is the observability matrix is given by the following. It's given by P naught is equal to, and then CT, and then C of T times A. Then you're going to have C of T, and it goes all the way to C of T, and then A of N minus 1. Where here, of course, N is the number of state variables, same thing as you had before. So if you have 3 state variables, you only go CT A to the power 2. So this is your number of state variables. Okay, now what we have is it's observable if and only if the determinant of PO is not equal to 0, which PO is the observability matrix, of course. So observable if and only if the determinant of PO is not equal to 0. Okay. So that's what we're going to say. So notice that the observability only depends upon C and A. It's not dependent upon B or D, just so you know. And so what we're going to have here is let's look at an example in order to better understand this. So remember up here how we had this. Determine the controllability. Let's look at the observability just from this matrix up here. So PO would be equal to, and then C of T is 1, 2. So 1, 2. And then now C of T times A. So what we're going to have here is just looking at our C of T times A. If I'm just writing that as a side note, it'd be 1, 2 times, and then 1, 3, 3, 1. So this would be 1 times 6. So 1 plus 6. So that's going to be 7. Then here we have 3 plus 2. So that's 5. So I got 7, 5. For my observability matrix, so the determinant of P0 is here. If you take the determinant, it'd be 5 minus 14, which is negative 9. So then it is observable. There you go. So we got the observability, we got the controllability. So notice that the determinant of our controllability matrix is not equal to 0, so that's why it's controllable. The determinant of the observability matrix is not equal to 0, so that's why it's observable. So we were able to get those two. So we see observability and we see controllability. Now, what we need to determine is when we have, we're going to try and design this. And so we want to design a controller for the system such that the controller and the system behave in the manner we want. And so what we're going to do here is there's sort of a little bit different of a, now when we're going to be using state space and they have a little bit different of like a feedback scheme, I want to say, within your system. And so what we're going to see for full state feedback design, that's what I'm going to call this, full state feedback design, just so you don't confuse it with our other, they have an input to the controller. And so we're going to see R here is our input to our controller. So we have a controller here. And then we're going to have our U, which is in between here, which is our control signal, right? It's coming out of the controller. And then it goes to our plant, which is our system. And then it's going to go to the output Y. So this is hooked back to the controller. And so our control signal is given by U here. And then you're going to notice that it's going to be equal to negative K T X plus R, because we're going to have a K gain here. So our U is going to equal to R minus kt and then x. This is going to be the feedback, which is going to be the negative kt, and then we're going to find our state variable. So right now, this was the simplified design, but the actual design of what it looks like within our system is, remember how we just started with like the input. We didn't have like any of this weird feedback. And so for a single input, single output with state feedback, it's going to look like the following. So you can understand why that equation comes into being. It's going to have the summing block here in the feedback. So this feedback is going to be given by our K, our gain. And then it's going to go through here. And so from the signal, we're going to have our B. And then it's going to go through summing block. And then here we're going to have our A, of course. So here's going to be our A. And then it's going to be connected here. And then we're going to have our 1 over S. And then this is our X. Okay, then here's our C. And then we're going to have here, of course, our feed forward, what we're used to seeing. So here's our feed forward, D. And then it goes here to the summing block, where we're going to sum the two together and then to produce our output Y. Okay, so what we're going to have here is inside here, this is our states, X. And then at this part right here, we have our X dot. So this is familiar to us. We know this topology right here. That's what we're used to. But now we're introducing this other topology here, where this is the part that's new. So this is just given by your normal state space equation, but now we're having state space feedback to our system. And so what we're going to see here is if R of t is equal to 0, here's like a side note. If R of t is equal to 0, then we have full state feedback, right? You're just getting feedback from your states. That's it. Like you're just then full state feedback. And so what we're going to see here is within our design, this makes sense now how our equation, our U, which is right here, which is normally our input, is now going to be equal to our state feedback plus our input right here, R. And so now this is going to be our control input coming in, and we're still having our feedback. We're still going for the normal state space, but we're going to have our state space feedback here. So that's why now we have a K that's going to provide a certain amount of gain to our states to get them to the desired response. So now what we're going to have is, for a tracking problem though, what you're going to notice is that our RT, so if RT is equal to some constant, then we have a tracking problem. So say if, like, remember how the ball on plate system, we had to track to a certain position we wanted. So, to get to the desired point. So that would be like an example. It's equal to a constant here. You want to get to like 0.09 meters on the plate, and 0.09, 0.09, the coordinate that you want the ball to go to from the origin. So that's where this would be a tracking problem. And so now that we saw that, what we have to do is we have to understand how this changes our state space representation of our system. So let's look at the normal. I think it's best if we compare these sort of side by side to understand how this is happening, to see why it is the way it is. So here, what we're going to have is, remember, our state space representation was given by the following equation: A of x plus b u. And then we have y is equal to c of t of x. So remember, for this system, what we saw is we saw u was equal to negative kt x plus r. And so what we're going to do is we're going to just substitute that into our equation. So this would be a of x plus b, and then it's going to be negative kt x plus r. Okay, so having that here, what we're going to see is we can represent that as a, because notice that the x will now be common to here. So I can write it as a minus, and then we're going to have our b kt, and then x, and then plus br. And so that's what we have here, but our y stays the same. So our state representation for full state feedback is a little bit different. Notice here that our x dot is equal to a minus bk, and then it's going to be t. So our vector here, and then of x plus br. So that's what we have up here, and then our y is equal to c of t x. So this is for full state feedback. This is your definition here. So that's what we have. So what we're going to do now is we need to find the transfer function with full state feedback. So that's the output over the input, right? And so what we're going to have here is we're going to have y of s all over our input, which our input here is r of s. And so if you do that here, what you're going to get is your g of s is equal to y of s over r of s, which is c of t, times si minus a plus bk, and then of t to -1, and then of b. So this is your transfer function. Here. So that's what describes your system. And so that is your full state feedback transfer function and the state space representation. And so now that we saw this, now what we're going to do is, why do we like full state feedback? Now we sort of have to dive in. Why are we using this for our system? So what we like to do is we like to design the value of k here, because k is what we have going back, right? We want to design k to assign the closed loop poles. It's also known as eigenvalue assignment problem pole placement. So we like to assign the poles of the system so that it becomes stable. So state feedback can move the poles, but has no effect on the zeros. And so what we're going to see here is that, remember how we had s of I minus a was in the denominator of our transfer function? I think it was, let me see, how we represented our g of s is equal to here. Well, isn't this the inverse? So technically, what we're going to see here is our poles of our transfer function. If you write that the same way, remember, you have to find the determinant of s. Sorry, wait, these are the cofactors all over the determinant, which this is the cofactors of si minus a plus bk, and then of t all over your determinant, right? That's how you find the inverse of a matrix. So this would be the determinant of si minus a plus bk of t, and then times vector b. And so what we're going to see is that, can't you determine where the poles are going to be? And you have 1 degree of freedom here, your k. By adjusting your k, you can change the poles of your transfer function, so you can make your system stable. And so this is why it's called the eigenvalue placement problem, or the pole placement problem. So what we're going to do is that controllability is preserved by state feedback, because remember, controllability depends on A and B, but observability is not preserved, because what we're going to see is observability is dependent upon A and C. And so what we're going to see is that we're going to have then an impact upon our C. So what's going to happen here is we're going to determine the location of the roots and use Ackermann's formula to determine the state feedback. So there's some definitions here that you sort of got to know, is that if you find the desired characteristic equation, because when you have to find where your poles are, you have to find where you want your system parameters are, right? So first you find your poles to determine your characteristic equation. So right here, the desired characteristic equation might be given by the following. Characteristic equation might be given by Q of S is equal to s to the power of n plus a to the n, s of n minus 1, and then plus, and then dot, 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 plus a1s plus a naught. And so the state feedback is given by, here we have k of t is equal to, and so here it's 0 and then dot, 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 0, 1, and then it's going to be your controllability matrix and then times Q of A, where this is determined by the number of state variables you have. This is number of state variables. And so what we're going to see here is that what we're going to have is a lot of times they might say, when you use Ackermann's, you might have to use Q of A. So Q of A is just equal to, and then instead of having your S, you just plug in A here. So plus A n, and then A to the n minus 1 plus dot, 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 plus A1 to capital A plus A naught. So that's for Ackermann formula. You might have to do that. So what we're going to do is we're going to look at an example where we have to place the poles where we want, and then we're going to use both Ackermann's and equating both sides to see like which one gives us like the ones we want for our specific poles. So let's look at an example where we're going to have to determine all of these factors and put it together. So starting from here, we're going to have, for an example, we're going to use the same system. So x dot is equal to 1, 3, 3, 1 of x plus 1, 0, and then of u. And then we had the y is equal to 1, 2, and then of x. So for this, we determined the controllability and observability already of this system when we were practicing with it. So what we got is for our controllability matrix, we got 1, 0, 1, 3. And then we found that the determinant of P of C was equal to 3. So it was controllable. And for the observability matrix, we got 1, 2, 7, 5. And we found that the determinant of this observability matrix was equal to -9. So therefore it was observable. So what we have to do is we need to determine the poles of the system. So where are our poles located? So in order to do this, what we have to do is we're going to have to find where these poles are actually located. And so looking at our system, remember, the poles are determined by the eigenvalues of our matrix A. And so remember how our eigenvalues are given by lambda, delta lambda is equal to the determinant of lambda in the identity matrix minus A. That's where we actually find the poles of our system. If you remember the transfer function, because we're going to be dealing with state feedback here, remember how we said the poles of the system are determined by our determinant down here? So that's why that's where poles of the system, poles of the transfer function. And so what we're going to see is that by doing that, we're going to have for ours lambda of the identity matrix minus A. So lambda minus 1. Then we're going to have 0 minus 3. Then we're going to have 0 minus 3. And then we're going to have lambda minus 1. Okay. So we need to find the determinant of this. And so what we're going to get here is we're going to get a lambda squared And then we're going to get minus 2 lambda, then plus 1, and then that's going to be minus, and then a 9. And so we're going to get lambda squared minus 2 lambda minus 8. Okay, so this is how we found our actual characteristic equation. But in order to get the poles, you set it equal to 0, right? So when lambda squared minus 2 lambda and then minus 8 is equal to 0, we're going to get a lambda minus 4 and a lambda plus 2. It's going to be equal to 0. So lambda 1 is equal to 4 and lambda 2 is equal to negative 2. Those are where your poles are located. So we found the poles of our transfer function. Now, what we have to do is we need to find our state feedbacking. So the next part is going to be, so this is part A, determine the poles of the system. The next one is going to be determine the state feedbackings such that the poles are located at S1, comma 2 is equal to negative 1 plus minus 2j. Okay, so here, remember, if you want to get your poles to a specific area, that means that your closed loop transfer function should be equal to, and then where are your poles? So that's the desired characteristic equation. So your S1, your S minus S1, like where you actually want your poles to be, and then S minus S1 conjugate, because these are the desired location of our poles. So S minus S1, then S minus S1 conjugate, of course. So here it's going to be S minus, so that'll be a plus 1, and then plus 2j, and then times S plus 1 minus 2j. So this will be our desired location for our poles. So that's going to be, when we do this, you're going to get an S squared plus 2S plus 5. Okay. So we got our desired location. So what we have to do now is we need to determine the gain in order to get to that desired location. So we found our characteristic equation. So after that, what you can do is after you find this desired characteristic equation, remember that your gain is going to be given by kt is equal to 0, and then dot, 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 and then 0, 1. So how many state variables we have? 2, right? So 0, and then it's going to go, so we only have 2, so it's going to be 0, 1. Length 2 here for number of state variables, and then your controllability matrix, the inverse of that, and then Q of A. So that is your gain vector. So what we're going to see is we're going to have 2 gains, right? Because we only have 2 actually here. So we're going to have K1, K2 is going to be equal to 0, 1. And then we have to find the inverse of our controllability matrix. So here's our controllability matrix here. In order to find the inverse of this matrix, remember, you have to do the 1 over the determinant, and then all the cofactors, then you have to do the transpose of that matrix. So to find PC negative 1, that's going to be 1 over the determinant, which is going to be just 3 minus 0. So that would just be 3. And then the cofactor is going to be negative 1, and then 1 plus 1. And then it's going to be blocking that out, you just get 3. And then next one's negative 1, 1 plus 2. Blocking that out, you get 0. Then here, negative 1, and then it's going to be 2 plus 1, and then you're going to get, here, blocking out 2, 1, you get 1. And then here, we're going to have negative 1, and then 2 plus 2, and then blocking those out, you're going to just get row 2, you'll just get 1. So, then you take the transpose of that. So I have 1/3, and then in here, I have 3. Then I have 0. Then I have negative 1. Then I have 1. And you take the transpose. That's your inverse. So what we're going to see here is you're going to have 1/3. And then you're going to have 3, 0, negative 1, 1. And so we're going to get 1, 0, negative 1/3, and then 1/3. Okay. That's your controllability, the inverse for this one. And so now we need to plug that in. So your K1, your K2 is going to be equal to, and then remember this is just inverse and then cube A. So 0, 1, and then multiplied by 1, 0, negative 1/3, and then 1/3. And then here we're going to have cube A, which cube A you just plug in. This is your cube S, right? So plug in A here. So I'm sort of just going to write that off to the side here. So your cube A is going to equal, well, A times A. That's what this, because it's going to be A squared plus 2 of A plus 5. And then this is a constant, so you just multiply by the identity matrix to add with that matrix. So what I'm going to get here is if you do matrix A times matrix A, you're basically going to see that when you actually do that, I don't have it written down, so we'll just solve it. It's going to be here, cube A is going to equal 1, 3, 3, 1 times 1, 3, 3, 1, and then plus, and then it's going to be 2 times 1, 3, 3, 1, plus, and then we're going to have 5, 0, 0, 5. Okay. So here, when we solve this, you're going to notice when you do the matrix multiplication, this would be 1 plus 9, so that'd be 10. And then we're going to have 3 plus 3, so that'll be 6. Then we're going to have 3 plus 3, so that'll be 6. Then we're going to have 9 plus 1, so that'll be 10. And then here we're going to have plus. So this would be 2, and then plus 5 would be 7. And then we're going to have 6, and then plus 0. And so then we're going to have 6 plus 0, and then we're going to have 2 plus 5, which would be 7. So cube A is going to equal 10 plus 7 is 17, then 12, then 12, and then 17. Okay. So here, what we're going to have here is then we have 17, 12, 12, 17. Now, what we have to do is we're going to have to do our matrix multiplication. So 0 times 1. So that'd just be 0. Then 0 times 1. So we just get 1/3. So this would be 0, 1/3. Then we're going to have 17, 12, 12, 17. It's going to be your K1 and your K2. And then what you're going to notice here is that you're going to get, here this will turn out to be 0 times 17 plus 1/3 times 12 is 4. Then you're going to get 0 times 12 plus 1/3, so that'll be 17/3. So comparing that with what you should have gotten is 4 and 17/3. Let's see if that was correct. 4 and 17/3. Yes, that is correct. What you have is 4 and then 5.66. Yep, so that's how you would determine your K1 and your K2 values for the state feedback gains to satisfy your system here. Now that we got that, that is pretty much to get your poles where you want. So now that we saw a way to do that, we have to look at state estimators now in order to determine how we can estimate a system if we're not really given it. So state estimators are a little more difficult in the sense that they require a little bit more. So we'll look into those in order to determine how we solve one of those equations. Oops. Okay, so for the state estimator, what we're going to see here is if the state variables aren't available, so we don't have access to our state variables, then we use a state estimator. So basically, this just means if the state variables aren't available. If aren't available. Then we use the state estimator. Okay, so what we're going to have is basically what we have to do is that when we have our system, we only know like our input and our output. We really don't know what's happening in between our system too well. And so say that we're given the state space representation AX plus B U, and we have Y is equal to CT and then X. What you're going to notice here is that A, B, and C are known. So A, comma B, comma C are known. So we know those parameters, and the input and the output are known. So I'll just write that here, U of T and Y of T, and we know these parameters are known, but we don't know X of T. X of T is unavailable. It's not known. And so we don't know the states, but we know the other stuff. And so what we can do here is we're going to estimate the X of T with our input or output in the system dynamics here. And so we're going to denote the estimate. So we're going to try and estimate X of T from our input, our output, and the state dynamics, or sorry, and the system dynamics. Which are A, B, and C. And so here, what we're going to notice is that the estimate is going to be X hat of T. That's going to be our estimate of, so the estimate of X of T is X hat of T. And so we're going to try and make that estimate basically to have zero error. And so what we're going to notice within our system is we're used to seeing it such that we have our input, so our U coming into our system. So this is the block diagram, and it goes through B, of course, and then it goes through the summing block. And then here we have our state variables, and then we have our 1 over S in order to get our states, and then our X, and then we're going to have our C here, and then we get our output. And then it feeds back here through A, and then this is going to go through to give us our parameters. So A describes our system here, along with B and C. And so then what we're going to do down here is from this, we can't determine our states X. And so we're going to make an estimate. So we're going to take the output, which is available to us. And then we're also going to take the input, which is available to us. So the input is going to go through still B. And because we know B, and then it goes through the summing block here. And so we're going to feed in, we know A. So we're going to feed in A. And then we have here 1 over S. We know, of course, that's going to occur, go from our X, and then I'm going to have a little hat to represent the estimate, and then this is just your X hat, of course, right here. And then that's just because it's the estimate of the states. Then it goes through C here, and then it's going to go through this way. So this is your Y hat, the estimate of your output, and you're adding in, so you're finding the error between it, and the error you're going to adjust this L in order to decrease the error. And then here we go. So in contrast to the state feedback, this one, you're changing the parameter L, sort of to minimize the error between your output, your actual output versus like what your estimated output is. So you're going to try and minimize the error between the two so you get to your desired output. And so the estimation error between your current and your state, the actual state, so your actual state minus the estimated state here. That's defined as your estimation error. And so what you're going to notice basically is when you do the derivative of that, you're going to see that your estimation error is going to be equal to A minus LC and then transpose of your air signal. And so the changes in the air signal, that's what you're going to see basically happening. So the dynamic of the air signal is given by this equation. So we're going to design our L in this equation to make the estimate as close to the state as possible. So we want this to go to 0. So we're going to design L so that the estimate, we change the error as quick as possible so that it goes to 0. So what's going to happen is we're going to design L to make E of t as small as possible. That's really just what. So what we're going to do is we're going to make the poles here to the left of the j omega axis super fast so that it goes to 0. And so what we're going to notice is that within our system is that the feedback basically here is what we're going to have to do within our system is notice the following between, I just want to define these two parameters because I think the x, so looking here at our actual is that we get our x dot is equal to ax, which here ax, and then plus b, and then u, and then so what we're going to see is u, substituting that in. So from the system above, we're going to get x is equal to, so the derivative of our states is equal to ax plus b, then negative kt, and then we're going to see here that and then x hat plus r. And then here, our output is getting given by CT of x. So this equation is because what this is represented by is our u. Because remember, you use negative kt and then x and then plus r. And then so I think he made a mistake in his notes because that doesn't. Hey, Fernando, do you agree with me real quick? Shouldn't this one, because this one's not the estimate, so I don't think the hat should be on this one.
Let me see. So BU, and
I
this
don't
is
think that
you're substituting mu equals to negative KTX, right? That's what U is equal to.
the
U,
estimator,
mu,
because this is from the original plan, but if this is the estimated one, like here similarly for the estimator,
ooh, that's a tough one. I'm not too sure to be honest.
okay, we'll just go with it because his matrix is defined in that way, so we'll just, I'm assuming he's right on this, so just go with it. Then what we have here is this is our actual system here. So this is our system, but the estimator is given by, what we're going to see here is that the x, and then this is going to be the hat dot, is equal to, and what we're going to have here instead is it's a little more different because it's going to be a of x hat, because of course that's coming in a of x hat, and then we're going to have plus b of u, and then we're going to have plus L and then y minus y hat. Okay, so right here, you can see those relationships, how it's coming in A of x hat minus, or sorry, plus B of u, right? And then we're going to have plus L times y minus y hat. So this one makes sense. And we're going to have, if you just simplify this down to its bits, you're going to get L C of t x plus A minus B k of t, and then plus L C of t, and then x hat plus BR. And so what we're going to notice here is this is just a simplification of it. So he just wrote it in matrix form for us for our estimator versus our actual system. And so if we wrote this in the state space representation, you're going to see that these two can be given by your x dot and your x hat dot. And that's going to be equal to, if you just copy over what we wrote on the last slide, you're going to see negative bk and then t, and then this would be a minus bk of t, and then plus LC of t, and then it's going to be x and x hat, and then it's going to be plus b and then br. So they're both having the input vector parameters. And so what we're going to notice is our output is given by c of t and then 0 and then x and x hat. X and x hat. Okay. And so what we're going to see from here is recall that E is equal to x minus x hat. So if you substitute that in here, instead of saying x hat, if we do E instead, what we're E dot, sorry, you're going to notice that we're going to still have, it's going to be A minus B and then KT and then BKT, and then just have these formulas down on your cheat sheet. Not gonna lie, A minus L and then CT, and then here it's X and then E, and then what we're going to notice is plus B 0 of R. Okay, so Y is equal to, and then CT, and then 0, and then we're gonna have X and then E. So here what you're going to notice is that within our system specifically is we're going to have to notice that from this is our state space representation of the system. So this, if he has us having to determine the Leuenberg estimator, this is how you would design the L for it for your state estimator. So I would just have these two state space representations if he were to ask you, so you have those defined for your actual parameters. Those would be the two. Make sure you just have on your cheat sheet in case. But what you're going to see is putting your state estimator doesn't affect the original state feedback nor the eigenvalues. So you just have to design it such that like it doesn't impact it. But what we're going to notice is we're going to look at an example where we have our state space representation, and what we're going to do is we're going to just go from there and find the values of our L, our values of our actual system. So I'm just going to walk us through an example and just see how it goes. So here, this is the one with the state estimator. So we're given a system here. So the inverted pendulum, what you have to know is we're operating around equilibrium so that we can linearize our system. So he gave us the system equations here for our actual one. And so he chose state variables specifically as the position. And then you're going to see the velocity, because that's a derivative of position, the angle, and then the angular velocity. And so he wrote the 4 state variables, and he actually then just took his equations. Basically, he just wrote 4 equations for state variables, because from here, he just found his y double dot t and his theta double dot t, got them, and then wrote his state space representation. So from the state space representation, he got his output equation. For his output, he was looking specifically at the position of the car. And so that was the first state variable. And so you want to hold the angle so the pendulum doesn't fall. It's just hold up right. It doesn't bend over to the right or left. So that's why the angle is 0. And so we only have access to the position of the cart. And so that's the issue. And so we need to hold the angular, which is state variable 3, at 0. And how can we do that with only measurements of the position? So from his state space representation, he found the eigenvalues. Because remember, the eigenvalues are found by your characteristic equation, which remember, your eigenvalues are defined as determinant of SI minus A when that is equal to 0. So he just did S of I minus A here, so minus is A, and he got his open loop poles. Then he found his controllability and his observability matrices. From here, he determined that the system was controllable and observable. And so remember, we had our open loop poles here. And so what we're going to see is our open loop system. You're going to have a pole at 0, 2 of them, and then you're going to have 1 at 10 and 1 at -10. And so the closed loop characteristic equation, what you want to do here is we're going to notice that our we want to make sure, notice that we have a pole on the right-hand side. So we want to move all the poles to the left-hand side and make it stable. So we have 4 poles, so that's why we have a 4th order here. We have a 2nd order times a 2nd order. These are going to place a lot further away, so they have no impact upon our system. So here we chose 2 poles, such that they were closer to our j omega axis. So here he designed it such that we had them about 0.4 from our, so 0.8 times 0.5, that's going to give you 0.4, so it's negative 0.4. And then so he chose these values, so it was closer to the j omega axis. And then he chose these values such that it was further away. So here it's occurring at -8 here. So he has these poles at -0.4 and these at -8. So they're further away. And so what happened is he found the state feedback gain. Because remember, the state feedback gain, we have 4 state variables. So that's why it's 0, 0, 0, 1. He found the inverse matrix of the controllability one and then plugged in Q of A. Because this is the desired, and so he plugged in A instead of S with his parameters he chose. And so that's how he got his state feedback here. Now, so that was only on the controller because he could design a controller. So remember, the observer, you want it to be faster so you can do your estimation. So the observer characteristic equation is given by the following format. Notice that he just squared it because he just had, you have to have 4 poles, so that's why he just squared it, so he got 4. And he chose the observer be further away, so he chose it way out. So here in green, they're like way further from the other ones. So here, C1's 32, so it's about -16. So they're twice as fast because remember here it's occurring at -8 because 16 it's at -2 zeta omega n, so zeta omega n's 8 here. So he chose it to be twice the distance because the observer has to be twice as fast. So instead of 16, he chose 32 here. So 32 here. And then using Ackermann's formula, he found L. So remember, L is defined here specifically as the following, where it's P of A. And so your P of A, he plugged in A here, and then P naught, and then so that's this observability matrix, and then taking the inverse of it. And then we have 4 state variables. So that's why this is 4 long. So it's 0, 0, 0, 1. And so just remember your K and your L, how they're defined. They're very similar. So he is able to design his controller and he is able to design his observer. And from there, he got his values. So that notice, the open loop system, we had 2 poles at the origin and we had one at -10, one at 10. He found his controller such that he wanted it to be at -0.4, and then he had it a little up and down. And then he had the other ones a little further away. And then his observers were twice the distance away. So this was at -8. So they were at -16, and there was 2 of them repeated at each of those. And so notice the system performance when you use the state feedback using the full state versus the estimated. Your full state, notice that it goes, your estimated goes faster in terms of getting to the desired value 0 from your full state feedback. And so that's why he's able to get to 0. So the pendulum balances because the angle returns to 0. And so that pretty much summarizes everything. So let me stop